Right now, at this very moment, a bubble of destruction could be forming somewhere in the universe, expanding outward at the speed of light, rewriting the laws of physics as it goes. You would have no warning. The bubble would arrive at light speed, which means you could never see it coming. One instant you exist, the next instant the fundamental forces holding your atoms together simply stop working the way they should. Everything ends, not in billions of years, not after the stars burn out, but now, possibly in the next second, possibly before you finish this sentence. This is not science fiction. This is a prediction that emerges directly from our best understanding of quantum field theory and the fundamental nature of reality. In 1977, physicists Sidney Coleman and Frank DeLucia published a paper describing what they called vacuum decay, or false vacuum decay. They were investigating the stability of the quantum vacuum, the lowest energy state of empty space itself. What they discovered was profoundly disturbing. If the universe exists in what is called a false vacuum, rather than a true vacuum, then quantum mechanics allows for a spontaneous transition to the lower energy state. This transition would begin at a random point in space and expand outward as a bubble at light speed. Inside the bubble, the laws of physics would be fundamentally different. The constants that govern particle masses, force strengths, and the very structure of matter would all change. Outside the bubble, everything continues as normal. At the boundary between them, everything gets destroyed. The mathematics behind this prediction are solid. Coleman and DeLucia were not speculating wildly. They were following the equations of quantum field theory to their logical conclusion. The quantum vacuum is not actually empty. It is a roiling sea of virtual particles constantly popping into and out of existence, borrowing energy from the uncertainty principle. This vacuum has an energy associated with it. If our universe happens to exist in a state where the vacuum energy is not at its absolute minimum, then we live in what physicists call a false vacuum. Think of it like a ball sitting in a shallow valley on a hillside. It looks stable. It can sit there for a very long time, but it is not in the lowest possible position. The true minimum energy state, the true vacuum, lies farther down the hill. Quantum mechanics says that even without any external push, the ball can spontaneously tunnel through the barrier and roll down to the true minimum. When it does, everything changes. Here is where the numbers get uncomfortable. After Coleman and DeLucia published their work, physicists began calculating whether our universe might actually be in a false vacuum state. The calculations depend on measurements of fundamental particle properties, especially the mass of the Higgs boson. The Higgs field is what gives particles their mass, and its properties determine the shape of the vacuum energy landscape. In 2012, scientists at the Large Hadron Collider near Geneva discovered the Higgs boson and measured its mass at approximately 125 billion electron volts, or about 125 GeV. This measurement was precise to within about 0.5%. It represented one of the great triumphs of experimental physics. It also created a significant problem. When physicists plugged that measured Higgs mass into their calculations of vacuum stability, the results were disturbing. The most careful analyses, published between 2012 and 2015 by research teams including Giuseppe Di Grassi, Dario Butazzo, and colleagues, showed that with a Higgs mass of 125 GeV and the measured mass of the top quark at about 173 GeV, the standard model vacuum appears to be metastable. Not stable, not immediately unstable, metastable. The universe sits in a false vacuum that could, in principle, decay at any moment. The probability of such a decay occurring in any given cubic meter of space in any given second is extraordinarily small, perhaps something like 10 to the power of minus 100 or less. But it is not zero. And the universe is very large. With roughly 10 to the power of 80 atoms in the observable universe, spread across billions of light years, even extremely unlikely events become possible over cosmic timescales. The calculations suggest that if nothing else changed, the vacuum might remain stable for something like 10 to the power of 100 years or more. That is a 1 followed by 100 zeros. For comparison, the current age of the universe is only about 13.8 billion years, or roughly 10 to the power of 10 years. So the expected lifetime of a metastable vacuum is unimaginably longer than the current age of the cosmos. You might think this means we are safe. You would be wrong. The probability is an average. Quantum mechanics is fundamentally probabilistic. The decay could happen in 10 to the power of 100 years, or it could happen right now. There is no schedule, no countdown, no warning system. What makes this particularly unsettling is that the decay is not just unlikely, but also irreversible and absolute. Once a bubble of true vacuum forms, it expands at the speed of light. Nothing can stop it. Nothing can escape it. The bubble wall converts false vacuum to true vacuum as it passes, releasing the energy difference. The exact amount of energy depends on the difference between the false and true vacuum states, but estimates suggest it could be enormous, possibly equivalent to several times the mass energy of the false vacuum region itself. This energy gets released at the bubble wall, creating a shockwave of unimaginable violence. Even before that shockwave hits you, the changing vacuum inside the bubble would alter the fundamental constants of nature. The strength of the electromagnetic force might change. The masses of electrons and quarks might shift. The atoms that make up your body, held together by electromagnetic forces between electrons and nuclei with their current masses, would simply cease to exist in their current form. Physicists verified this scenario through increasingly sophisticated calculations over the past 4 decades. After Coleman and DeLuccia's original paper, researchers including Michael Stone, Michael Dine, and many others refined the analysis, considering corrections from quantum field theory, the effects of gravity on vacuum decay, and the influence of additional particles beyond the standard model. In the 1980s and 1990s, theorists explored how vacuum decay might have occurred in the early universe, potentially explaining aspects of cosmic inflation. In the 2000s and 2010s, precision measurements of particle masses from experiments at Fermilab and CERN allowed for increasingly accurate calculations of vacuum stability. Each new measurement narrowed the possibilities. The measured values consistently pointed toward metastability. The discovery of the Higgs boson in 2012 was the crucial piece. Before that, physicists could speculate about different Higgs masses and their implications for vacuum stability. A Higgs boson significantly heavier than 125 GeV would have implied a stable vacuum. A Higgs significantly lighter would have suggested immediate instability, which would be incompatible with the universe's continued existence. But the actual measured value of 125 GeV sits right on the knife edge between stability and instability. It places us in the metastable regime. This was not what most physicists expected or hoped for. It was what the data showed. Before you drift off, leave a comment. What time is it where you are right now, and where in the world are you watching from? The implications extend far beyond abstract theoretical physics. If the vacuum is metastable, then the universe exists in a state of precarious equilibrium. We are like a pencil balanced on its point, stable in principle but vulnerable to the slightest perturbation. High-energy events might trigger vacuum decay, colliding black holes, the Big Bang itself, interactions in the cores of neutron stars. Some physicists even worried before the Large Hadron Collider turned on that the high-energy proton collisions it produces might nucleate a vacuum decay bubble. The calculations showed this risk to be negligible, but the fact that serious scientists had to perform the calculations at all reveals how real the underlying physics is. Vacuum decay represents a fundamental limit on the longevity of complex structures in the universe. Stars will eventually burn out. Galaxies will drift apart. Black holes will evaporate over timescales of 10 to the power of 100 years. But if the vacuum is false, even the laws of physics themselves are temporary. The equations that govern chemistry, the forces that allow atoms to bond into molecules, the constants that permit stars to shine and planets to hold atmospheres, all of these exist only because we happen to be in a particular vacuum state. Change that vacuum state and everything changes. The anthropic principle suggests that we should not be surprised to find ourselves in a universe where the vacuum has not yet decayed. After all, in universes where it already did decay, there would be no observers to notice. We necessarily exist at a time and place where the vacuum remains in its false state. But this observation does not make us safe, it just means we are lucky. So far. The statistical nature of quantum mechanics means that every second that passes without vacuum, decay does not make the next second any safer. The probability remains constant. It is like flipping a coin that is weighted to come up heads 10 to the power of 100 times before showing tails. Most likely, you will flip heads, essentially, forever. But there is no guarantee. Tails could come up on the very next flip. Physicists call this a Poisson process. Events occur randomly and independently at some average rate. The fact that no event has occurred yet tells you nothing about when the next event will happen. The universe has no memory of how long the vacuum has remained stable. Each moment stands alone, equally probable, equally vulnerable. This is one of the strangest aspects of our cosmic situation. We live in a universe that appears fundamentally stable on human timescales. The sun rises, atoms hold together. The laws of physics remain constant from one day to the next. Yet underlying this apparent stability is a mathematical structure that admits the possibility of instantaneous total transformation. The solidity of matter is an illusion resting on the temporary stability of the quantum vacuum. And that stability is not guaranteed by any law of physics. It is simply a probabilistic statement. The vacuum probably will not decay in the next second. Probably not in the next billion years. But somewhere in the infinite vastness of space or the endless stretch of time, the decay could occur. And when it does, a bubble of new physics will begin expanding, consuming everything in its path, until it has converted the entire reachable universe into a new state. This brings us to a profound question about the nature of physical law itself. We tend to think of the laws of physics as eternal, unchanging, fundamental. But quantum field theory suggests otherwise. The laws we observe are contingent on the particular vacuum state we inhabit. Change the vacuum, and you change the laws. There may be other vacuum states, other possible configurations of the quantum fields that permeate space, where electrons have different masses, where the strong nuclear force is stronger or weaker, where gravity behaves differently at small scales. These alternative physics regimes are not forbidden. They are simply not the regime we currently occupy. But they exist as possibilities in the mathematical structure of quantum field theory. And if a bubble of one such regime forms and begins to expand, it brings those alternative laws with it. The calculations describing vacuum decay involve some of the most sophisticated tools in theoretical physics. Quantum field theory in curved spacetime. instanton solutions representing quantum tunneling through potential barriers, renormalization group equations describing how coupling constants change with energy scale, semi-classical approximations to path integrals. These are not simple concepts, but the basic conclusion is straightforward. The vacuum can decay. If it does, the decay propagates at light speed. And inside the bubble, physics is different. These three facts, derived from well-tested theories, combine to create a scenario that is both scientifically rigorous and existentially terrifying. The universe could end in a fraction of a second, and we would never see it coming, because the destruction travels at the maximum possible speed, the speed of information itself. What happens at the boundary of such a bubble involves physics at the most extreme scales. As the bubble expands, the vacuum inside sits in a lower energy state than the vacuum outside. The energy difference must go somewhere. It gets released at the bubble wall, where false vacuum converts to true vacuum. Estimates suggest the energy density at this wall could be enormous, potentially exceeding the Planck energy density of about 10 to the power of 113 joules per cubic meter. At these densities, space-time itself becomes unstable. Quantum fluctuations in the geometry of space and time become significant. The smooth continuum we experience at everyday scales breaks down into a foaming, fluctuating structure where distances and durations lose their classical meanings. The bubble wall is not just a discontinuity in the vacuum state. It is a region where space-time itself tears and reforms, where the Einstein equations of general relativity cease to provide an accurate description, where a complete theory of quantum gravity would be needed to understand what actually occurs. This quantum gravity regime is something we cannot yet fully describe mathematically. We have candidate theory, string theory, and loop quantum gravity among them, but no definitive experimental evidence to guide us. So the precise details of what happens at a vacuum decay bubble wall remain uncertain. But the broader picture is clear enough. The bubble expands at light speed. At its boundary, the energy release is catastrophic. Inside the bubble, the constants of nature are different. These facts alone are sufficient to conclude that any complex structures, atoms, molecules, organisms, stars, planets, would be destroyed as the bubble passes. The precise mechanism of destruction might be through the direct shockwave of energy release. It might be through the failure of electromagnetic and nuclear forces inside the bubble to bind particles together as they do in our current vacuum. Either way, the result is the same. The mechanism driving this transformation operates at the most fundamental level of reality, in the quantum fields that fill all of space. These fields are not material objects. They are mathematical entities, functions that assign a value to every point in space-time. The electron field, for instance, has a value everywhere in the universe. When that field is excited above its ground state at a particular location, we observe a particle we call an electron. The photon field, when excited, produces particles of light. The Higgs field, discovered through its excitation at the Large Hadron Collider, gives mass to other particles through their interactions with it. Every particle in nature corresponds to a quantum field, and the properties of those particles depend on the configuration of their associated fields. The vacuum state is the configuration where all these fields sit at their lowest possible energy. Or rather, it should be. Here is where it gets strange. Quantum field theory allows for situations where the fields appear to be at a local minimum energy, a valley in the energy landscape. But there exists a deeper valley somewhere else. The fields are stuck in the wrong configuration. Not because any force holds them there, but because transitioning to the true minimum requires passing through a region of higher energy first. Classically, this would be impossible. A ball cannot roll uphill without an external push, but quantum mechanics introduces tunneling. A quantum system can spontaneously transition from one state to another, even when the intermediate states have higher energy, by temporarily borrowing that energy from the uncertainty principle. The probability of such tunneling depends exponentially on the height and width of the barrier between the false and true vacuum states. A high, wide barrier makes tunneling rare. A low, narrow barrier makes it more probable. The Higgs field plays the central role in vacuum stability because its potential energy function determines whether our vacuum is true or false. The potential can be visualized as a landscape, with the Higgs field value on one axis and the potential energy on the other. In a stable universe, this landscape has a single deep valley at zero field value. The Higgs field sits at the bottom and stays there. But the actual shape of the potential depends on quantum corrections from all the other particles in the standard model. Virtual particles constantly appear and disappear in the vacuum, and their fleeting existence affects the Higgs potential through quantum loop effects. The top quark, being the heaviest known fundamental particle at about 173 GeV, contributes significantly to these quantum corrections. Its mass pulls the Higgs potential in a particular direction. When physicists calculate the full corrected potential using the measured Higgs and top quark masses, they find that at very high field values, far beyond what we observe in everyday physics, the potential develops a second minimum. The Higgs field could, in principle, sit in that distant valley instead of the one it currently occupies. The transition between these two minima involves the Higgs field suddenly jumping from its current value of about 246 GeV to a much larger value, possibly 10 to the power of 17 GeV or more. This is not a gradual process. Quantum tunneling is instantaneous in the sense that there is no smooth path through the intermediate states. The field simply transitions from one configuration to another through what physicists call an instanton, a solution to the field equations that exists in imaginary time. This sounds abstract, and it is, but the mathematical machinery is well established. Instantons were first used to describe tunneling in ordinary quantum mechanics. They were later applied to quantum field theory by physicists including Alexander Polyakov, Gerard 't Hooft, and Sidney Coleman himself. The instanton describing vacuum decay has a specific shape. It represents a spherical bubble of true vacuum, with a certain radius determined by the properties of the potential, surrounded by false vacuum. Once this bubble forms through quantum tunneling, it begins to expand. The expansion occurs because the true vacuum inside the bubble has lower energy than the false vacuum outside. This energy difference exerts an outward pressure on the bubble wall. At the same time, the bubble wall itself has surface tension, which resists expansion. For very small bubbles, the surface tension dominates, and the bubble would collapse back to nothing. But there is a critical radius determined by the ratio of surface tension to energy difference, beyond which expansion becomes favorable. Bubbles that quantum tunnel into existence with radii larger than this critical value will expand indefinitely. Bubbles smaller than the critical radius collapse. The probability of tunneling into a critical-sized bubble is what determines the overall decay rate of the false vacuum. This probability depends on an exponential factor involving something called the bounce action, a quantity calculated from the shape of the potential energy barrier. Larger bounce actions mean lower tunneling probabilities and longer expected vacuum lifetimes. The numbers involved in these calculations are extreme. The bounce action for vacuum decay in our universe, given the measured Higgs and top quark masses, is estimated to be around 400 or more. This translates to a tunneling probability per unit volume per unit time of roughly 10 to the power of minus 400 in Planck units. Converting to more familiar units of cubic meters and seconds makes the probability even smaller, something like 10 to the power of minus 600 or less. These numbers are so small that they lose intuitive meaning. But here is what they imply in practice. The probability that a decay bubble will form somewhere in the observable universe in the next second is utterly negligible. The probability that one will form in the next billion years is still essentially zero. The probability that one will form in the entire future history of the universe, extending trillions upon trillions of years into the future, remains very small. But it is not zero. And in an infinite universe or over infinite time, events with non-zero probability eventually occur. Why conventional understanding fails to capture the strangeness of this situation has to do with our intuitions about stability. In everyday life, stable means permanent. A table is stable. It will not spontaneously collapse. A house is stable. It will not suddenly disintegrate. But these classical notions of stability rely on the fact that classical objects have well-defined energy barriers protecting them from decay. A table would need to be actively destroyed by some external force. Quantum systems are different. They can spontaneously tunnel through energy barriers, transitioning from metastable states to more stable states without any external trigger. The false vacuum is metastable in exactly this quantum sense. It is not permanently stable. It is stable only probabilistically, only on average, only until the moment when a random quantum fluctuation nucleates a bubble of true vacuum. At that moment, stability ends. And because the bubble expands at light speed, carrying new physics with it, there is no defense against it and no escape from it. Think of the false vacuum like a super-saturated solution. Water can be cooled below its freezing point without solidifying, remaining liquid at temperatures where ice should form. But this supercooled water is not stable. It is waiting for a nucleation site, a speck of dust or a scratch on the container, anything that can trigger crystallization. Once crystallization begins at one point, it spreads rapidly through the entire volume, converting liquid to solid. The false vacuum is similar. Space exists in a state that is not its absolute minimum energy configuration. It persists in this state because transitions to the true minimum are rare. But once a transition occurs at any point, once a bubble of true vacuum forms, that bubble expands and converts the surrounding space to the new configuration. The analogy is imperfect because supercooled water crystallizes at much less than light speed, and the phase transition does not change the laws of physics. But the basic pattern is the same. Metastability, nucleation, rapid expansion, complete transformation. The measurable effects of living in a metastable vacuum are subtle because the expected lifetime is so long. If the decay rate is 10 to the power of minus 600 per cubic meter per second, then even across the entire observable universe, containing roughly 10 to the power of 80 cubic meters, and even over billions of years, the chance of decay remains vanishingly small. We do not observe any consequences of metastability in everyday physics. Atoms remain bound, forces remain constant. The vacuum does not flicker or fluctuate in ways we can detect. The metastability is revealed only through theoretical calculations, through working out the implications of measured particle masses for the shape of the Higgs potential. This is one of the remarkable aspects of modern physics. We can know something profound about the stability of the entire universe, not by observing the universe directly, but by measuring the mass of a single particle, the Higgs boson, in a laboratory. Detection of actual vacuum decay, if it were occurring anywhere in the observable universe, would be dramatic. A bubble expanding at light speed from some distant point would eventually reach us. But we would have no warning of its approach. Light from the bubble's formation point would travel toward us at the same speed as the bubble itself. We might, in principle, detect photons emitted from the bubble wall, high-energy radiation produced by the energy release at the boundary between true and false vacuum. These photons would arrive at exactly the same instant as the bubble wall itself. There would be no time to react, no time to understand what was happening, no time to do anything. One moment, business as usual. The next moment, the laws of physics change and everything ends. This lack of warning is baked into the structure of spacetime. Light speed is the speed of causality, the maximum rate at which information can propagate. A disturbance moving at light speed carries its own first announcement of its existence. Physicists have considered whether any precursor signals might leak out ahead of a vacuum decay bubble. Perhaps gravitational waves or some exotic particle moving at light speed, but emitted in advance of the main bubble wall. The calculations suggest no such precursors exist. The bubble formation is a quantum event, instantaneous and localized. Before the bubble forms, there is nothing to signal. After it forms, the bubble expands at light speed, and nothing can travel faster to warn us. The only possible detection would come from observing vacuum decay occurring in distant parts of the universe, far enough away that the bubble has not reached us yet. If such a bubble existed billions of light years away and had been expanding for billions of years, we might detect the radiation from its formation point, arriving at light speed from the past. We might observe a spherical region of space, constantly growing, where the spectroscopic signatures of atoms appear different, where the constants of nature have shifted, where physics operates under different rules. No such observation has ever been made. Astronomers have surveyed the cosmos in exquisite detail. They have mapped the cosmic microwave background, the relic radiation from the early universe, with angular resolution better than 0.1 degrees across the entire sky. They have catalogued billions of galaxies, measured their spectra, determined the abundances of elements in distant stars. Nowhere in all this data is there any evidence of a region where physics differs from what we observe locally. The fine structure constant, which characterizes the strength of electromagnetic interactions, appears the same in galaxies 10 billion light-years away as it does in laboratories on Earth. Measurements by teams using the Very Large Telescope and the Keck Observatory have constrained any variation in this constant to less than 1 part in a million over most of cosmic history. The mass of the electron, inferred from spectroscopic lines in distant quasars, remains constant to similar precision. The laws of physics appear universal across the observable universe. This uniformity tells us something important. If vacuum decay has occurred anywhere in the observable universe during the roughly 13.8 billion years since the Big Bang, the bubble has not expanded far enough to reach us or to enter the portion of space we can observe. The observable universe extends about 46 billion light-years in all directions, accounting for cosmic expansion. A vacuum decay bubble forming at the moment of the Big Bang and expanding at light speed would now be about 13.8 billion light-years in radius, measured in co-moving coordinates. Such a bubble would be visible if it formed within the observable universe. The fact that we see no such bubble places constraints on the decay rate. The probability of decay per unit volume per unit time must be low enough that no bubbles have formed within our cosmic horizon in the past 13.8 billion years. The calculations of vacuum stability, which predict decay rates around 10 to the power of minus 600 or less, are consistent with this observational constraint. They predict that vacuum decay should be extraordinarily rare, rare enough that we would not expect to observe it. The history of how physicists came to understand vacuum instability stretches back to the early development of quantum field theory itself. An understanding that history reveals how seemingly abstract mathematics connects to the ultimate fate of physical reality. The theoretical framework emerged in stages, beginning in the 1940s when physicists first developed the mathematical tools to describe quantum fields. Richard Feynman, Julian Schwinger, and Shinichiro Tominaga independently formulated quantum electrodynamics between 1947 and 1949, creating the first complete quantum field theory. Their work described how electrons and photons interact through the exchange of virtual particles, and it introduced the concept of vacuum fluctuations. The quantum vacuum, they showed, was not empty but filled with particle-antiparticle pairs constantly appearing and disappearing. This was revolutionary. The vacuum had structure, it had energy, and most importantly, it could exist in different states. By the 1960s, physicists had extended these ideas to the strong and weak nuclear forces, building what would become the standard model of particle physics. Sheldon Glashow proposed a unified theory of electromagnetic and weak interactions in 1961. Steven Weinberg and Abdus Salam independently developed this idea further in 1967, introducing what we now call the Higgs mechanism. The Higgs mechanism explained how particles acquire mass through their interaction with a field that permeates all of space. This field, the Higgs field, must have a non-zero value in the vacuum. Not zero, but some finite number, approximately 246 GeV. This vacuum expectation value of the Higgs field determines particle masses throughout the standard model. The electron mass, the W and Z boson masses, the quark masses, all arise from their couplings to this background field value. The possibility that the vacuum might not be unique, that other configurations might exist, became clear once physicists understood the Higgs mechanism fully. In 1973, Sidney Coleman and Eric Weinberg published a paper analyzing the quantum corrections to the Higgs potential. They showed that quantum effects from virtual particles could dramatically change the shape of the potential energy landscape. What might appear to be a simple valley at the classical level could develop additional structure, additional minima, once quantum corrections were included. This opened the door to the concept of false vacuum. If quantum corrections produced multiple minima in the potential, the universe might sit in one minimum while a deeper minimum existed elsewhere. The question then became whether transitions between these minima could occur. Coleman addressed this question directly in 1937, collaborating with Frank DeLucia on the paper that first described vacuum decay in detail. They calculated the rate at which quantum tunneling could nucleate bubbles of true vacuum within a sea of false vacuum. Their method involved finding instanton solutions, configurations of the fields that minimize the action in imaginary time. The instanton represents the quantum tunneling process, and its properties determine the tunneling probability. Coleman and DeLucia's paper, titled Gravitational Effects on and of Vacuum Decay, extended earlier work on tunneling in quantum mechanics to the context of quantum field theory in curved spacetime. They showed that gravity affects the tunneling rate, generally making it easier for bubbles to form, but also limiting how large they can grow before expansion takes over. The paper remains one of the most cited in theoretical physics, referenced thousands of times in subsequent research. Through the 1980s and 1990s, physicists refined these calculations and explored their implications. Michael Stone published a detailed analysis in 1976 before Coleman and DeLucia on quantum tunneling in field theory. Curtis Callan and Sidney Coleman wrote a comprehensive review in 1977 that laid out the mathematical machinery. Alexander Vilenkin and others considered how vacuum decay might create new universes. with bubbles of true vacuum expanding to become entire cosmos separated from the parent false vacuum by event horizons. Andre Linde and others incorporated these ideas into theories of cosmic inflation, suggesting that the early universe might have undergone transitions between different vacuum states, with each transition releasing energy that drove exponential expansion. These were not idle speculations. They were attempts to understand real features of the universe: the flatness, the homogeneity, the origin of structure using the tools of quantum field theory. The 1990s brought precision measurements that began constraining the parameters relevant to vacuum stability. The top quark, predicted by theory but not yet observed, was discovered at Fermilab in 1995 by the CDF and D0 collaborations. They found it weighed about 173 GeV, making it by far the heaviest known fundamental particle, roughly 40 times heavier than the bottom quark and about 340,000 times heavier than the electron. This enormous mass has profound implications. The top quark couples very strongly to the Higgs field, and its quantum contributions to the Higgs potential are proportional to the fourth power of its mass. A top quark this heavy pulls the Higgs potential downward at high field values, creating the possibility of a second minimum. Physicists immediately recognized that vacuum stability would depend critically on the precise values of both the top quark mass and the eventual measured mass of the Higgs boson itself. The hunt for the Higgs boson intensified. The Large Electron-Positron Collider at CERN, operating from 1989 to 2000, searched for the Higgs without success, constraining its mass to be above 114 GeV. The Tevatron at Fermilab continued the search through the 2000s, narrowing the possible mass range but not finding the particle. Meanwhile, construction of the Large Hadron Collider proceeded. The LHC is a circular accelerator 27 kilometers in circumference, buried 100 meters underground beneath the French-Swiss border. It accelerates protons to energies of 6.5 trillion electron volts each, then smashes them together at collision points surrounded by massive detectors. The engineering required to build this machine was extraordinary. Superconducting magnets cooled to 1.9 Kelvin colder than outer space bend the proton beams around the ring. Each collision produces temperatures and energy densities not seen in the universe since the first trillionth of a second after the Big Bang. The LHC began operations in 2008, shut down after a magnet failure, and resumed in 2010. By 2011, the two main detectors, ATLAS and CMS, were each collecting billions of proton collisions, searching through the debris for signs of new particles. On July 4, 2012, both collaborations announced the discovery of a new particle with a mass around 125 GeV. Further measurements confirmed it was the Higgs boson, the particle associated with the Higgs field. The discovery was celebrated worldwide. Peter Higgs and François Englert, two of the theorists who predicted the particle in 1964, received the Nobel Prize in Physics in 2013. But while the discovery itself was a triumph, the measured mass value created immediate concerns about vacuum stability. Physicists had been preparing for this moment. In the months and years before the Higgs discovery, theoretical groups had published papers calculating what different Higgs masses would imply for vacuum stability. A 2012 paper by Giuseppe De Grassi, along with colleagues including Stefano Di Vita, Joanne Elias Miro, and others, provided detailed calculations showing that a Higgs mass near 125 GeV placed the universe right at the boundary between stability and metastability. They computed the effective Higgs potential at high energies using renormalization group equations, which describe how coupling constants change with energy scale. At low energies, the potential has a single minimum near 246 GeV. But at energies around 10 to the power of 17 GeV, far above anything we can create in laboratories but relevant in the early universe or in extreme astrophysical environments, the potential develops a second, deeper minimum. The barrier between these minima is high enough that tunneling is extremely rare, giving the false vacuum a lifetime far exceeding the current age of the universe. But the barrier exists. The second minimum exists. We live in a metastable vacuum. Independent groups confirmed these results. A 2015 paper by Dario Buttazo and colleagues provided updated calculations incorporating the most precise measurements of the top quark mass and the Higgs mass, along with refined calculations of the quantum corrections. They found that the instability scale, the energy at which the second minimum appears, is approximately 10 to the power of 11 GeV, with significant uncertainty depending on the exact top quark mass. This energy is far below the Planck scale of 10 to the power of 19 GeV, where quantum gravity effects become important, but far above the electroweak scale of a few hundred GeV where the Higgs operates in everyday physics. The calculations required extraordinary precision. The fate of the vacuum depends on particle masses measured to within 1% or less, and on quantum corrections involving loops of virtual particles computed to 3-loop order or higher in perturbation theory. The technological breakthroughs enabling these measurements were themselves remarkable. The ATLAS and CMS detectors at the LHC are among the most complex scientific instruments ever built. ATLAS stands 25 meters tall and weighs 7,000 tons. It contains 6 different detector subsystems, each designed to measure different properties of particles produced in collisions. Innermost are silicon pixel and strip detectors that track charged particles with micron precision. Surrounding these are calorimeters that measure particle energies by absorbing them completely and recording the resulting shower of secondary particles. Outermost are muon chambers that identify muons, heavy cousins of electrons, as they pass through meters of steel shielding. CMS has a similar but distinct design, centered around a massive superconducting solenoid magnet that produces a field of 4 Tesla, 100,000 times stronger than Earth's magnetic field. The magnetic field bends the paths of charged particles, allowing precise measurement of their momenta. Measuring the Higgs mass required analyzing millions of collision events. The Higgs boson is unstable, decaying in about 10 to the power of minus 22 seconds into other particles. It cannot be observed directly. Instead, physicists look for characteristic patterns in the particles produced by Higgs decay. 2 photons emerging from a collision point with a combined mass of 125 GeV. 2 Z bosons, themselves decaying into 4 leptons with the right kinematic properties. The signal is tiny, perhaps 1 Higgs boson, produced for every billion collisions, buried in backgrounds from other standard model processes. Advanced statistical techniques, machine learning algorithms, and years of data collection were required to extract the signal with sufficient confidence. The final mass determination, combining data from multiple decay channels and both detectors, reached a precision of about 2%. That precision was sufficient to reveal the metastability. The evolution of theoretical understanding paralleled these experimental advances. In the decades between Coleman's 1977 paper and the 2012 Higgs discovery, physicists developed increasingly sophisticated tools for calculating vacuum stability. Early calculations used tree-level approximations, considering only the classical potential without quantum corrections. Later work included one-loop corrections, accounting for the effects of virtual particles circulating once through quantum loops. By the 2000s, 3-loop calculations became possible, incorporating effects that were third-order in quantum corrections. Each level of refinement changed the predictions slightly, but significantly. The difference between stability and metastability depended on terms that appeared only at 2-loop or 3-loop order. This is why precision mattered. A small change in the top quark mass, just a few GeV, could shift the instability scale by orders of magnitude or eliminate the instability entirely. Specific examples illustrate the sensitivity. If the top quark weighed 171 GeV instead of 173 GeV, and everything else remained the same, calculations suggest the vacuum would be absolutely stable. No second minimum would exist in the Higgs potential, even at arbitrarily high energies. If the top quark weighed 176 GeV, the instability would be more pronounced, the second minimum deeper, the tunneling rate higher. The measured value of 173 GeV sits right on the edge. Similarly, for the Higgs mass, a Higgs boson at 130 GeV would likely imply stability. A Higgs at 120 GeV would suggest immediate instability, incompatible with the universe's existence. At 125 GeV, we get metastability. The universe is stable enough to exist for billions of years, but not permanently stable. This fine-tuning troubles some physicists. Why should the fundamental parameters of nature conspire to place us exactly at the boundary between stability and instability? Some researchers propose that the standard model is incomplete, that new physics beyond what we currently understand stabilizes the vacuum. Supersymmetry, a theoretical framework doubling the number of fundamental particles, was long considered a leading candidate. Supersymmetric particles, if they existed with masses below about 1000 GeV, would contribute quantum corrections to the Higgs potential that could eliminate the instability. The LHC has searched extensively for supersymmetry. As of the early 2020s, no supersymmetric particles have been found. Mass limits now extend above 2000 GeV for many predicted particles. This does not rule out supersymmetry entirely, but it reduces its ability to explain vacuum stability. The new particles would need to be too heavy to affect the Higgs potential significantly at the instability scale. Other proposals invoke additional Higgs bosons, new forces, extra dimensions of space, or modifications to gravity at high energies. None have experimental support. The simplest interpretation of current data is that the standard model is correct and the vacuum is metastable. This metastability connects to the deepest questions about the structure of reality and our place within it. The vacuum is not just some abstract background, it is the stage on which all physical processes occur. Every interaction between particles, every force, every measurement takes place within the vacuum. When we say the vacuum has a particular energy, we are describing the baseline state of space-time itself. Change that baseline and you change everything built upon it. The constants we measure, the relationships between force strengths, the spectrum of particle masses, all depend on which vacuum state the universe occupies. We exist in a universe fine-tuned for complexity, where atoms can form, where chemistry works, where stars can shine for billions of years, providing stable energy sources for planetary systems. A different vacuum might not permit any of this. The connection to cosmic inflation reveals one of the great paradoxes. Inflation is our best explanation for why the universe appears so uniform on large scales. In the first fraction of a second after the Big Bang, according to inflationary theory, the universe underwent a period of exponential expansion, growing by a factor of at least 10 to the power of 26 in a time interval, shorter than 10 to the power of minus 32 seconds. This expansion was driven by the vacuum energy of a field, often called the inflaton field, which sat in a false or slowly rolling vacuum state. As the inflaton field eventually transitioned to its true minimum, the vacuum energy was released, converting into the hot bath of particles and radiation that became the matter and energy we observe today. Inflation is, in essence, a controlled vacuum decay. The early universe existed in a false vacuum. That false vacuum decayed, and the decay produced our universe. Here is the paradox. Inflation requires a false vacuum to function. The false vacuum's energy drives the exponential expansion. When that false vacuum decays, inflation ends, and the hot Big Bang begins. But if our current vacuum is also false, just metastable rather than immediately unstable, then we might still be in an inflaton-like state. Not the same inflaton field that drove primordial inflation, but another field, perhaps the Higgs itself, sitting in a metastable configuration. If this vacuum eventually decays, what happens? Does the entire universe undergo another phase transition, another period of rapid evolution, another transformation of physical laws? Or does the decay simply destroy structure locally wherever it occurs, creating bubbles of new physics within the old, fragmenting the cosmos into incompatible domains? The broader cosmological context makes this even stranger. Our universe is expanding and the expansion is accelerating. Observations of distant supernova in 1998 by two independent teams, the Supernova Cosmology Project led by Saul Perlmutter, and the High Z Supernova Search Team led by Brian Schmidt and Adam Rees, revealed that galaxies are receding from us faster than simple inertial expansion would predict. Something is pushing space apart. Physicists attribute this acceleration to dark energy, a component of the universe with negative pressure that comprises about 69% of the total energy density. The simplest explanation for dark energy is that it represents the energy of the vacuum itself, the cosmological constant that Einstein introduced and then famously rejected. If dark energy is vacuum energy, then the current vacuum already possesses a significant energy density, roughly 10 to the power of -9 joules per cubic meter. This raises an immediate problem. Quantum field theory predicts that the vacuum energy should be much larger, perhaps 10 to the power of 113 joules per cubic meter, a value determined by summing the zero-point energies of all quantum fields up to the Planck scale. This is 120 orders of magnitude larger than what we observe. The discrepancy between predicted and observed vacuum energy is the worst prediction in the history of physics, sometimes called the cosmological constant problem. No one knows why the vacuum energy is so small. Various mechanisms have been proposed to cancel most of the expected contribution, but none are convincing. If the vacuum is metastable and sits in a false minimum, then perhaps the energy we observe represents the difference between the false vacuum energy and the true vacuum energy, with most of the expected contributions somehow cancelled. But this is speculation. The cosmological constant problem remains unsolved. The accelerating expansion has its own implications for vacuum decay. As the universe expands and accelerates, distant regions recede from us faster and faster. Eventually, regions beyond a certain distance, currently about 16 billion light-years away in co-moving coordinates, will recede faster than light. Not because they move through space faster than light, which is impossible, but because the space between us and them expands fast enough that light cannot cross the growing gap. These regions pass beyond our cosmic event horizon. We will never receive light or information from them again. They become causally disconnected from us. If a vacuum decay bubble formed in such a region, it would expand at light speed within that region, but we would never see it. The bubble and our observable universe would exist in separate causal domains, forever isolated by the accelerating expansion. In this sense, cosmic acceleration protects us from distant vacuum decays. But it does not protect us from decays that nucleate nearby, within our cosmic horizon. Measuring the stability of the vacuum involves indirect methods because we cannot directly probe energies of 10 to the power of 17 GeV or higher, where the instability appears. Instead, physicists measure particle properties at accessible energies, a few hundred GeV to a few TeV at the LHC, and extrapolate to high energies using renormalization group equations. These equations describe how coupling constants and masses change as you examine physics at different energy scales. The fine structure constant, for instance, is not truly constant. At low energies, it has a value of about 1 divided by 137. At higher energies, it increases slightly, reaching about 1 divided by 128 at the mass of the Z boson. This running of coupling constants is a quantum effect, arising from vacuum polarization and other processes involving virtual particles. The Higgs self-coupling, which determines the shape of its potential, also runs with energy. At low energies, it has 1 value. At high energies, it can become negative, indicating that the potential develops a second minimum. The extrapolation from measured values to high-energy predictions introduces uncertainties. The renormalization group equations are differential equations that must be integrated over many orders of magnitude in energy. Small errors in the initial conditions, the measured masses and couplings at low energy, can grow as you integrate upward. Additionally, the equations themselves involve approximations. Physicists typically compute them to 3-loop order, meaning they include effects from quantum corrections involving up to 3 loops of virtual particles. 4-loop and higher corrections exist but are extremely difficult to calculate. The uncertainties from unknown higher-order terms, combined with experimental uncertainties in the measured input parameters, mean that predictions about vacuum stability have significant error bars. Current best estimates suggest the instability appears around 10 to the power of 11 GeV, but the range extends from 10 to the power of 10 to 10 to the power of 13 GeV, depending on precise top and Higgs masses. Secondary effects complicate the picture further. Gravity, for instance, plays a subtle role in vacuum decay. Coleman and DeLuccia's original 1977 paper incorporated gravitational effects, showing that gravity changes the tunneling rate and the critical bubble radius. In flat spacetime without gravity, the critical radius is determined solely by the surface tension of the bubble wall and the energy difference between true and false vacuum. But in curved spacetime, gravity adds an additional contribution. The energy density inside the bubble gravitates, curving spacetime around it. For false vacuums with positive energy density and true vacuums with lower but still positive energy, this gravitational effect generally makes tunneling slightly easier. The bubble formation rate increases. However, the calculations also show that extremely large energy differences can prevent bubble formation entirely. If the true vacuum has much lower energy than the false vacuum, the bubble would create such strong gravitational fields that it collapses into a black hole before it can expand. This places constraints on possible vacuum energy differences. Our position in this cosmic structure is worth considering carefully. We find ourselves in a universe where the vacuum is metastable, with a lifetime much longer than the current cosmic age but not infinite. This seems like an unlikely coincidence. Why this particular configuration? Anthropic reasoning offers one answer. In universes where the vacuum is immediately unstable, structure never forms. Atoms do not bind, stars do not ignite, life never arises. No observers exist to wonder about vacuum stability. We necessarily find ourselves in a universe where the vacuum has lasted long enough for complexity to emerge. This does not require the vacuum to be absolutely stable, only metastable with a sufficiently long lifetime. A vacuum with an expected lifetime of 10 to the power of 100 years is functionally equivalent to a perfectly stable vacuum for any observers arising within the first 10 to the power of 10 years. Both allow complex structures to form and persist for cosmically long periods. But anthropic reasoning has limits. It explains why we do not observe immediate instability. It does not explain why the measured parameters place us so close to the boundary between stability and metastability. A universe with a slightly heavier Higgs boson would be stable. A universe with a slightly lighter one would be unstable. We happen to live in the narrow range between them. Some physicists suggest this is evidence for a multiverse, an ensemble of universes with different vacuum states and different physical constants. In such a multiverse, all possible values of the Higgs mass would be realized somewhere. We observe the value we do because it is compatible with our existence, and only universes with parameters allowing observers will be observed. Other physicists find this reasoning unsatisfying, arguing that it explains nothing and makes no testable predictions. The debate continues. Location matters in another sense as well. The vacuum decay rate depends on the local energy density and gravitational field. In flat, empty space far from matter, the rate is determined by the zero temperature, zero density tunneling probability calculated by Coleman and DeLucia. But near massive objects where spacetime is curved and energy densities are high, the situation changes. Strong gravitational fields affect the Higgs potential, potentially raising or lowering the barrier between true and false vacuum. High temperatures, such as those in the cores of stars or in the early universe, provide thermal energy that can assist tunneling over the barrier rather than through it. Collisions between particles at high energy can momentarily create localized regions where the Higgs field reaches large values, sampling the parts of the potential where the second minimum exists. These considerations led some physicists to worry that the Large Hadron Collider might trigger vacuum decay. If proton collisions at the LHC created conditions where the Higgs field transiently occupied the high-energy region of the potential near the second minimum, might that nucleate a bubble of true vacuum? Several detailed studies addressed this question before the LHC turned on. The conclusion was reassuring. Cosmic rays, high-energy particles from space, strike Earth's atmosphere constantly, producing collisions at energies matching or exceeding those at the LHC. These collisions have been occurring throughout Earth's history. If they could trigger vacuum decay, it would have happened already. The fact that we still exist demonstrates that LHC energy collisions do not pose a risk. Moreover, detailed calculations show that even if the LHC created a microscopic region where the Higgs field briefly explored the unstable part of the potential, such a region would collapse back to the false vacuum almost immediately. Creating a bubble large enough to expand requires overcoming the surface tension, and random thermal or collision-induced fluctuations do not provide enough energy for that. The situation in the early universe was different. In the first moments after the Big Bang, temperatures exceeded 10 to the power of 15 Kelvin, corresponding to energies above the instability scale. The Higgs field was not yet settled in its current minimum. It was in thermal equilibrium with all the other fields, fluctuating wildly. Why did the universe not decay to the true vacuum then, when conditions were hot and energetic enough? The answer involves the finite temperature effective potential. At high temperatures, thermal effects modify the shape of the potential, generally making the false vacuum more stable. The particles in the hot plasma contribute to an effective mass for the Higgs field, raising the barrier between true and false vacuum. As the universe cooled below the instability scale, the thermal contribution decreased, and the zero temperature potential took over. By then, the Higgs field had already settled into the false minimum. Thermal fluctuations at lower temperatures were no longer sufficient to push it toward the true minimum. The field became trapped in the metastable state, where it remains today. This history suggests a kind of cosmic selection effect. The early universe, hot and dense, naturally evolved toward the false vacuum. Once there, the cooling and expansion locked the field in place. Universes that happened to settle into the true vacuum directly would look different, with different particle masses and force strengths. Universes that settled into even higher false vacua might have decayed rapidly, transitioning through multiple phase transitions before reaching a stable or metastable configuration. We observe the configuration we do because it is the one that resulted from our particular cosmic history. This is not a coincidence arranged for our benefit. It is a consequence of how quantum fields behave under the conditions present in the early universe. The metastability emerges naturally from the interplay between high-temperature stabilization and low-temperature quantum tunneling. The tension reveals itself most clearly when physicists compare predictions from different theoretical approaches. The first method uses what is called the effective field theory framework. This approach starts with the measured values of particle masses and coupling constants at the energy scales accessible to experiments, roughly a few hundred GeV to a few TeV. Physicists then employ renormalization group equations to extrapolate these values to higher energies, calculating how the Higgs self-coupling evolves as you probe deeper into the structure of spacetime. Teams including Giuseppe De Grassi, Dario Butazzo, and their collaborators have performed these calculations to 3-loop precision, meaning they include quantum corrections involving 3 nested loops of virtual particles. Their results suggest the Higgs self-coupling becomes negative somewhere around 10 to the power of 11 GeV, indicating the development of a second minimum in the potential. The vacuum decay rate they calculate is roughly 10 to the power of minus 400 to 10 to the power of minus 600 in Planck units, corresponding to an expected lifetime exceeding 10 to the power of 100 years. The second method takes a different route entirely. Instead of extrapolating from measured values using perturbative calculations, some physicists use lattice gauge theory, a computational approach that discretizes space-time into a grid and calculates field configurations numerically. Lattice calculations do not rely on perturbation theory, which approximates quantum effects as small corrections to classical behavior. Instead, they compute the full quantum behavior from first principles by evaluating path integrals on a computer. For the Higgs potential, lattice calculations can, in principle, determine the shape of the potential at high energies without extrapolation, directly computing the quantum corrections that determine whether a second minimum exists. However, lattice calculations of the Higgs potential at high energies are extraordinarily challenging. The computational cost scales poorly with increasing energy, and results remain preliminary. Some lattice studies suggest the instability might appear at different energies than perturbative calculations predict, or that the barrier height might be different, changing the tunneling rate by orders of magnitude. The disagreement between these methods stems partly from uncertainties in the input parameters. The effective field theory approach depends sensitively on the measured top quark mass. The current world average value from combining measurements at the Tevatron and LHC is approximately 172.76 GeV, with an uncertainty of about plus or minus 0.3 GeV. This seems like a small error, less than 0.2%, but the vacuum stability calculation depends on the top quark mass to the 4th power in some terms. A change of 1 GeV in the top quark mass can shift the instability scale by a factor of 10 or more. If the top quark actually weighs 172.4 GeV, rather than 173.1 GeV, both within current uncertainties, the predicted instability scale changes from 10 to the power of 11 GeV to perhaps 10 to the power of 12 GeV, and the tunneling rate changes by dozens of orders of magnitude. the expected vacuum lifetime could shift from 10 to the power of 100 years to 10 to the power of 300 years, or vice versa. These numbers are both incomprehensibly large, but the difference matters conceptually. It determines how close we are to the boundary between metastability and absolute stability. The Higgs boson mass introduces similar uncertainties. The current combined measurement from ATLAS and CMS gives 125.25 GeV, with an uncertainty of about plus or minus 0.117 GeV. This represents extraordinary precision, but again, small changes propagate through the vacuum stability calculation. A Higgs mass of 125.1 GeV versus 125.4 GeV, both consistent with measurements, yields different predictions for the high energy behavior of the self-coupling. The difference might determine whether the potential develops a second minimum at all, or, if it does, whether that minimum is deeper or shallower than predicted. Current uncertainties leave room for multiple scenarios. The vacuum might be absolutely stable if we happen to be on one side of the measurement error bars. It might be more metastable than currently estimated if we are on the other side. Beyond experimental uncertainties lie theoretical uncertainties. The renormalization group equations used to extrapolate coupling constants to high energy are known to three-loop order. This means physicists have calculated the effects of quantum corrections involving up to 3 nested loops of virtual particles circulating through Feynman diagrams. But 4-loop, 5-loop, and higher-order corrections also exist. They are simply too difficult to calculate completely. Physicists estimate the size of unknown higher-order corrections by examining the pattern of how corrections grow at each order. Typically, each additional loop contributes a correction smaller by a factor of the fine structure constant, roughly 1 divided by 137, times some numerical factor. This suggests 4-loop corrections change the running of the Higgs self-coupling by perhaps 1 or 2% compared to 3-loop results. That might sound negligible, but when you are extrapolating over 15 orders of magnitude in energy, from 100 GeV at the LHC to 10 to the power of 17 GeV at the instability scale, even tiny corrections at each step accumulate into significant shifts in the final prediction. Different groups estimate these theoretical uncertainties differently, leading to variations in predicted instability scales ranging from below 10 to the power of 10 GeV to above 10 to the power of 13 GeV. This 3 orders of magnitude spread might seem enormous, but on the logarithmic scale of high-energy physics, it represents relatively modest disagreement. All groups agree that if an instability exists, it appears at energies far beyond the reach of any conceivable particle collider. All agree that the tunneling rate is extraordinarily small, too small to pose any practical danger. The disagreement concerns exactly how small and whether the instability exists at all given measurement uncertainties. Why both methods should agree but do not reveals something fundamental about the challenges of quantum field theory. Effective field theory and lattice gauge theory are, in principle, equivalent descriptions of the same physics. Both are based on the Standard Model. Both should yield identical predictions when calculated correctly and precisely. The fact that they currently give different results indicates that at least one approach contains approximations or errors that matter at the level of precision required for vacuum stability calculations. Effective field theory relies on perturbation theory, treating quantum corrections as small deviations from classical behavior. This works well when coupling constants are small, but breaks down when they become large. Near the instability scale, some coupling constants in the Standard Model grow large enough that perturbation theory becomes questionable. Higher-order corrections might not be small. The series of quantum corrections might not converge rapidly. Lattice calculations avoid this problem by computing the full quantum behavior without perturbative approximations, but they introduce their own issues. The discretization of space-time onto a finite lattice creates artifacts systematic errors that must be carefully controlled. Extrapolating lattice results from the energy scales accessible to current computers to the much higher energies relevant for vacuum stability requires assumptions that may not be valid. The vacuum metastability itself helps explain some aspects of the discrepancy. If the universe sits very close to the boundary between stability and metastability, then any approach attempting to determine which side of the boundary we are on must be extraordinarily precise. Measurement errors, theoretical approximations, unknown higher-order corrections, and lattice artifacts all become critical. Asking whether the Higgs self-coupling becomes negative at 10 to the power of 11 GeV or remains positive is like asking whether a pencil balanced on its point will fall left or right. The answer depends on details too subtle to measure easily. A tiny imperfection in the pencil, an unmeasured air current, a quantum fluctuation in the atoms of the tabletop, any of these could determine the outcome. Similarly, vacuum stability depends on the precise values of parameters we can measure only imperfectly, and on quantum corrections we can calculate only approximately. The implications for our theoretical models are profound. The standard model of particle physics, developed over decades and tested to extraordinary precision, appears to be mathematically complete and self-consistent. It successfully predicted the existence of the W and Z bosons, the gluon, the top quark, and finally, the Higgs boson. Every particle it predicted has been found. Every interaction it describes has been verified. No experiment has revealed any deviation from standard model predictions at accessible energies. This success is remarkable, but the vacuum metastability suggests the standard model, while accurate, is not the whole story. A truly fundamental theory should not predict its own downfall. If the vacuum is metastable, the standard model contains the seeds of its own destruction, a mathematical possibility that the theory itself will cease to apply when the vacuum decays. This seems philosophically unsatisfying. Many physicists interpret vacuum metastability as evidence that new physics must exist beyond the standard model, even if we have not detected it yet. This new physics would modify the Higgs potential at high energies, eliminating the instability, or at least making it less severe. Supersymmetry was long considered the leading candidate for such new physics. Supersymmetric particles contribute additional quantum corrections to the running of the Higgs self-coupling. Corrections that can be large enough to change the sign from negative to positive, converting metastability to stability. But, as mentioned earlier, the LHC has not found supersymmetric particles. Mass limits now exclude the simplest versions of supersymmetry. More complicated models with heavier supersymmetric particles remain possible, but they lose their ability to stabilize the vacuum because the new particles are too heavy to significantly affect the running of couplings at the instability scale. Other proposals for new physics face similar challenges. Additional Higgs bosons could modify the potential. New heavy fermions or gauge bosons could contribute quantum corrections that shift the running. Extra dimensions of space could alter how couplings evolve with energy. But all of these ideas require new particles or new forces, and none have been detected. The absence of any signal for physics beyond the standard model at the LHC, combined with the measured values of the Higgs and top quark masses suggesting metastability, creates a puzzle. The standard model appears complete and self-contained, requiring no additional particles at accessible energies. Yet it also appears metastable, suggesting it cannot be the final theory. How do we reconcile these facts? One possibility is that the metastability is telling us something about the multiverse. If our universe is one among many in an eternally inflating cosmological landscape, then different universes would have different values of fundamental constants. Most would be stable or immediately unstable. A small fraction would be metastable with very long lifetimes, long enough for complexity and observers to emerge, but not infinitely long. We observe a metastable vacuum because that is the type of universe where observers like us can exist and ask questions about vacuum stability. This anthropic explanation requires accepting the reality of the multiverse, which many physicists find unsatisfying because it makes no testable predictions about our specific universe. Another possibility is that the metastability is genuine, that the vacuum will eventually decay, but that this decay is not catastrophic. Perhaps the transition to the true vacuum occurs smoothly rather than through expanding bubbles. Perhaps the true vacuum is only slightly different from the false vacuum, changing constants by small amounts rather than radically altering physics. Perhaps conscious observers could survive such a transition, adapting to the new laws as they emerged. These speculations remain highly uncertain. The calculations of Coleman and De Lucia suggest that vacuum decay via bubble nucleation is violent and destructive. But their calculations assumed specific properties of the potential. Different potential shapes might allow gentler transitions. We do not know. The stakes extend beyond academic questions about quantum field theory. If the vacuum is metastable, then the laws of physics governing our existence are temporary, not just contingent on the particular history of our universe, but actively unstable, subject to spontaneous transformation without warning. Every constant we measure, every relationship we discover between physical quantities, exists only because we happen to observe the universe during a period of metastable equilibrium. The reliability of those laws over cosmic timescales becomes questionable. Can we extrapolate our physics billions of years into the future with confidence? Can we predict the far future evolution of the cosmos if the very rules might change? These questions have practical implications for long-term thinking, for speculations about the ultimate fate of life and intelligence in the universe, for our understanding of our cosmic context. The disagreement between different calculation methods means we do not even know for certain that the vacuum is metastable rather than stable. The measurements place us near the boundary. Theoretical uncertainties blur that boundary. We might be in a stable vacuum that will last forever, with the appearance of metastability arising from measurement errors or uncalculated higher-order corrections. Or we might be in a metastable vacuum that is more unstable than current estimates suggest, with decay rates orders of magnitude higher than predicted, though still far too low to pose any near-term threat. Resolution requires better measurements and better calculations. The high luminosity LHC, an upgrade scheduled to run through the 2030s, will collect 10 times more collision data than the current LHC, improving measurements of the Higgs and top quark masses by factors of 2 or more. Future colliders, if built, could push measurements to even higher precision. Theoretical progress on 4-loop calculations and improved lattice methods could reduce theoretical uncertainties. But even with perfect measurements and perfect calculations, a deeper question remains. The vacuum stability calculation tells us what is possible, not what is certain. It gives us a probability per unit volume per unit time. That probability is so small that we expect the vacuum to persist far longer than the current age of the universe. But quantum mechanics is fundamentally probabilistic. The decay could happen at any moment, and the fact that it has not happened yet tells us nothing about when it will. This irreducible uncertainty baked into the structure of quantum theory itself means that some aspects of our cosmic future are simply unknowable. The counterintuitive nature of vacuum decay begins with a simple fact that contradicts everyday experience. Empty space is not empty. The vacuum, the state we think of as containing absolutely nothing, actually possesses energy, structure, and dynamics. This reverses our basic intuition about nothingness. We imagine a perfect vacuum as the absence of everything, a blank canvas with zero properties. But quantum field theory reveals that what we call empty space is actually the ground state of all quantum fields, a state of minimum energy that is not zero energy. Virtual particles constantly pop into existence and vanish again, borrowing energy from the uncertainty principle for brief moments. These fluctuations are not just mathematical abstractions. They produce measurable effects. The Casimir effect, first predicted by Hendrik Casimir in 1948 and experimentally confirmed in 1997 by Stephen Lamoureux, demonstrates that two uncharged metal plates placed very close together in a vacuum experience an attractive force. This force arises because the vacuum between the plates contains fewer virtual photon modes than the vacuum outside, creating a pressure difference that pushes the plates together. The vacuum is not merely active, it has weight. The cosmological constant, the term Einstein introduced to his field equations and later regretted, represents the energy density of empty space itself. Current measurements suggest this energy density is approximately 5.96 times 10 to the power of minus 10 joules per cubic meter. This seems vanishingly small, barely 10 to the power of minus 26 kilograms per cubic meter, when converted to mass via Einstein's E equals mc squared. But multiply that tiny density by the volume of the observable universe, roughly 4 times 10 to the power of 80 cubic meters, and you get a total vacuum energy equivalent to about 10 to the power of 54 kilograms. For comparison, all the ordinary matter in the observable universe, every star, planet, gas cloud, and atom, totals only about 10 to the power of 53 kilograms. The vacuum outweighs matter by an order of magnitude. Dark energy, which accelerates cosmic expansion, is likely just another name for this vacuum energy. The emptiest substance in existence dominates the gravitational dynamics of the cosmos. Here is where it gets backwards. We think of stability as permanence, solid, unchanging, reliable. But in quantum mechanics, the most apparently stable configurations can be the most precarious. A false vacuum looks perfectly stable. Everything within it behaves according to consistent laws. Particles have fixed masses. Forces have constant strengths. Nothing changes from moment to moment. Yet mathematically, this stable-seeming state sits in a local minimum of the potential, not the absolute minimum. It is like a ball resting in a shallow crater on the side of a hill. The ball is not moving. It could sit there for eons, but it is not in the lowest possible position. One quantum fluctuation, one sufficiently unlikely tunneling event, and the ball drops to the valley below. The most stable appearing universe can be unstable at its foundation. The detailed analogy that captures this situation involves supercooled water, but extended to reveal deeper implications. Pure water can be cooled several degrees below 0 Celsius without freezing if cooled carefully, without vibrations or impurities. The water remains liquid at temperatures where ice should exist. This supercooled state is metastable. The molecules want to form ice crystals, which have lower energy, but they cannot coordinate the transition without a nucleation site to start the crystallization. Drop a single ice crystal into supercooled water, and the entire volume freezes almost instantly. The ice crystal provides a template. Water molecules near it align into crystalline structure, releasing energy as they do so. That energy and structure propagate outward, converting liquid to solid throughout the container in seconds. The false vacuum is analogous to supercooled water. Space sits in a configuration with higher energy than the true minimum. It persists in this state because transitions are rare. But once a transition nucleates anywhere, it expands rapidly, converting the surrounding space to the lower energy configuration. But the analogy breaks down in important ways, and those breakdowns reveal the true strangeness. When water freezes, it remains water. H2O molecules rearrange into a different structure, but the fundamental forces holding hydrogen and oxygen atoms together do not change. The electromagnetic force that binds electrons to nuclei operates identically in ice and liquid water. When the vacuum decays, the fundamental forces themselves change. Inside a true vacuum bubble, electrons might have different masses. The strength of electromagnetism might be different. The ratio between the electromagnetic and strong nuclear forces might shift. These are not rearrangements within fixed laws. These are changes to the laws themselves. A better analogy might imagine supercooled water, where freezing not only converts liquid to solid, but also changes the chemical bonding rules, making water molecules unable to form H2O anymore, transforming hydrogen and oxygen into different elements with different properties. That is the scale of change vacuum decay represents. Observational evidence for vacuum metastability is indirect but compelling. We do not observe vacuum decay occurring anywhere in the visible universe. No regions of altered physics have been detected, but the very fact that the measured Higgs and top quark masses place us at the boundary between stability and metastability constitutes evidence. The probability that random chance would put us exactly at this boundary, given the vast range of possible values these masses might have taken, is extremely low. Some calculations suggest we sit within a few % of the critical boundary, a few GeV difference in particle masses, and we would clearly be on one side or the other. Why are we balanced so precisely on the edge? One interpretation is that we are not precisely balanced at all. We are metastable, and metastability is a generic outcome for universes in our region of the cosmological landscape. Most universes are either stable with comfortable margins or unstable and short-lived. A substantial fraction are metastable with very long lifetimes. We observe a metastable universe because that is where observers can exist. Simulations of vacuum decay provide another form of evidence, though they model the process rather than observing it directly. Physicists use computational tools to solve the equations describing how a bubble of true vacuum would nucleate and expand. These simulations start with the calculated Higgs potential, including all quantum corrections from standard model particles. They identify the instanton solution, the spherical bubble configuration that minimizes the action and represents the most likely tunneling pathway. They calculate the bounce action, which determines the tunneling probability. Then they simulate what happens after a bubble forms. The bubble wall expands outward at close to the speed of light, decelerating slightly due to surface tension and interactions with any matter it encounters. Behind the wall, inside the bubble, the Higgs field takes on its new value corresponding to the true vacuum. Particles entering this region would experience different masses and coupling constants. The simulation shows how the bubble grows, consuming space, converting false vacuum to true vacuum kilometer by kilometer, then megaparsec by megaparsec, eventually encompassing galaxy clusters, superclusters, and ultimately the entire observable universe given enough time. These simulations reveal features not obvious from simple calculations. The bubble wall is not infinitely thin. It has a characteristic width, typically around the inverse of the mass scale of the Higgs boson, roughly 10 to the power of -18 meters. Across this width, the Higgs field transitions from its false vacuum value to its true vacuum value. The energy density at the wall peaks at values that could exceed 10 to the power of 30 joules per cubic meter or more. depending on the energy difference between vacua. This energy density surpasses anything found in ordinary matter. For comparison, the core of the Sun has an energy density around 10 to the power of 16 joules per cubic meter. A nuclear explosion produces energy densities reaching perhaps 10 to the power of 20 joules per cubic meter. The vacuum decay bubble wall exceeds both by many orders of magnitude. Anything passing through such a region would be destroyed not by heat or pressure in the conventional sense, but by the sudden change in particle masses and force couplings. Atoms would simply stop existing in their current form as the rules governing their structure changed. The statistical improbability of vacuum decay over observable timescales is staggering but easily misunderstood. The calculated decay rate of roughly 10 to the power of minus 600 per cubic meter per second means that if you could watch a single cubic meter of space for 10 to the power of 600 seconds, you might expect to see a bubble nucleate. For context, 10 to the power of 600 seconds is incomprehensibly longer than the current age of the universe. The universe is about 4.3 times 10 to the power of 17 seconds old. We're talking about timescales 10 to the power of 583 times longer. No human can conceptualize such durations. Yet this is the expected waiting time for a single cubic meter. The observable universe contains about 10 to the power of 80 cubic meters. This increases the probability by that factor, but we are still looking at expected timescales around 10 to the power of 520 seconds before a bubble nucleates anywhere in the observable universe. This is still unfathomably long, but here is the critical point. These are expected values, averages over many trials. Quantum mechanics is probabilistic. The actual decay could happen sooner or later. There is no schedule. Think about that for a moment. The universe has existed for 13.8 billion years without vacuum decay. This tells us almost nothing about whether decay will occur in the next second or the next billion years, or the next 10 to the power of 100 years. The probability is constant at every moment. Each second is independent. The vacuum does not remember how long it has already lasted. This is fundamentally different from aging processes in ordinary matter. A star exhausts its fuel over billions of years and eventually dies, but its death is predictable based on how much fuel remains. A radioactive nucleus decays with a characteristic half-life, but we can calculate probabilities based on how long it has already existed. Vacuum decay follows a memoryless process. The distribution of waiting times is exponential. Most likely, decay will not occur for timescales vastly exceeding the current cosmic age. But a small probability exists that it could happen now. Alternative frameworks for understanding vacuum stability have been proposed. Some involve modifying quantum field theory itself at very high energies. If the theory changes near the Planck scale of 10 to the power of 19 GeV, where quantum gravity effects become important, then extrapolations of the Higgs potential to energies above that scale might not be valid. String theory, for instance, suggests that particles are not point-like but extended objects, one-dimensional strings vibrating in multiple dimensions. The Standard Model would be an effective low-energy approximation to this deeper theory. At energies approaching the Planck scale, stringy effects could modify the running of coupling constants, potentially stabilizing the vacuum, even if Standard Model extrapolations suggest instability. But string theory remains unconfirmed experimentally, and it makes no specific testable predictions about vacuum stability that differ from Standard Model calculations at accessible energies. Modified theories of gravity offer another approach. General relativity might not be the complete description of gravity at all scales. Modifications like FR gravity where the Einstein-Hilbert action is replaced by a function of the Ricci scalar curvature, change how gravity affects vacuum decay. These modifications could alter the bounce action, changing the tunneling probability by factors large enough to convert metastability to stability, or vice versa. But again, these are speculative. No evidence currently supports modified gravity over Einstein's theory. The detection of gravitational waves by LIGO, starting in 2015 with waveforms matching general relativity's predictions to extraordinary precision, constrains possible modifications. Gravity appears to operate exactly as Einstein described, at least at the scales and energies we can probe. Some physicists have explored whether quantum gravity effects not yet understood might fundamentally alter the nature of vacuum decay. If space-time itself is not continuous at the Planck scale but discrete or foamy, then the smooth bubble expansion calculated by Coleman and De Lucia might not correctly describe what happens. Perhaps tunneling between vacuum states works differently when space-time geometry is quantized. Perhaps the very concept of a bubble wall expanding through space breaks down when space itself is not a smooth manifold, but a quantum superposition of geometries. These ideas remain highly speculative, far from being formulated into testable theories. They represent hopes that future discoveries in quantum gravity might resolve the vacuum stability problem in unexpected ways. Loop quantum gravity, an alternative to string theory that quantizes space-time geometry directly, suggests space has a discrete structure at the Planck scale. Space is not infinitely divisible, but has a minimum volume, roughly 1 cubic Planck length, about 10 to the power of minus 105 cubic meters. If this is correct, then asking about vacuum decay at scales smaller than the Planck length becomes meaningless. The instanton describing bubble nucleation has a size set by the Higgs potential, potentially much larger than Planck scale for the metastable vacuum in our universe. So loop quantum gravity effects might not directly affect the calculation, but they could influence how the bubble wall interacts with space-time geometry once formed, potentially slowing expansion or creating exotic structures at the boundary between true and false vacuum. The philosophical implications grow darker when you consider that vacuum decay is not just unlikely, but also completely unpredictable in principle. Even perfect knowledge of all particle masses, perfect calculations of all quantum corrections, and perfect understanding of quantum gravity would not tell you when the vacuum will decay. They would only give you a probability per unit volume per unit time. The actual timing is random, determined by quantum fluctuations that are intrinsically unpredictable. This is not unpredictability due to ignorance or insufficient information. It is unpredictability written into the laws of physics. The universe's ultimate fate in a metastable vacuum is fundamentally uncertain. No amount of scientific progress can remove that uncertainty. We can only calculate how unlikely different scenarios are, never eliminate any possibility entirely. The nature of the bubble wall itself and what happens there involves physics that may be forever beyond our ability to test experimentally. Yet, the mathematics describes it with strange precision. The measurement techniques that revealed vacuum metastability did not involve directly probing the Higgs potential at high energies. No particle collider can reach the energies of 10 to the power of 11 GeV or higher where the instability appears. The Large Hadron Collider, the most powerful accelerator ever built, reaches collision energies of 13 to 14 trillion electron volts, or 14 TeV. This is impressive by human standards, but remains 8 orders of magnitude below the instability scale. Direct measurement is impossible. Instead, physicists employ an indirect strategy that represents one of the great intellectual achievements of modern physics. They measure particle properties at accessible energies with extreme precision, then use mathematical tools to extrapolate those measurements to energies far beyond experimental reach. The reliability of this extrapolation depends on understanding how physical quantities change with energy scale, encoded in equations that have been tested and refined over decades. The primary instruments enabling these measurements are the ATLAS and CMS detectors at the Large Hadron Collider. ATLAS, which stands for a toroidal LHC apparatus, began recording collisions in 2009. The detector weighs 7,000 tons and stands 25 meters tall, roughly the height of an 8-story building. It contains approximately 100 million electronic channels, each recording signals from particle interactions. When protons collide at the center of ATLAS, they produce hundreds of particles that spray outward in all directions. The detector is organized in concentric layers, each designed to measure different particle properties. Innermost are silicon pixel detectors containing 92 million pixels, each 50 microns wide. These track the paths of charged particles, with precision approaching 10 microns, about 1/10 the width of a human hair. Charged particles bent by magnetic fields curve as they pass through the detector. The radius of curvature reveals the particle's momentum. High momentum particles curve less. Low momentum particles curve more. Surrounding the tracking detectors are calorimeters designed to measure particle energies by absorbing them completely. The electromagnetic calorimeter uses liquid argon as the active medium, with accordion-shaped electrodes made of lead and stainless steel. When high-energy electrons or photons enter, they create cascades of secondary particles, showers that deposit energy in the argon. The amount of ionization in the argon is proportional to the original particle's energy. This calorimeter can measure electron and photon energies from a few GeV to several TeV with precision better than 1% for high-energy particles. The hadronic calorimeter, positioned outside the electromagnetic one, stops particles like protons and neutrons that do not interact electromagnetically. It uses steel absorber plates alternating with plastic scintillator tiles that emit light when particles pass through. Together, these calorimeters capture nearly all the energy from a collision, allowing physicists to check whether energy is conserved and to identify particles that escape detection, like neutrinos, by observing missing energy. The outermost layer consists of muon chambers. Muons are heavy cousins of electrons, about 200 times more massive, and they penetrate matter much more easily than electrons. They pass through the calorimeters, through meters of steel shielding, barely slowing down. The muon system tracks their trajectories using arrays of gas-filled tubes and resistive plate chambers. By comparing muon tracks measured in the inner detector to tracks measured in the outer muon system, physicists can identify muons with extraordinary accuracy and measure their momenta with precision approaching 0.1%. This precision is crucial for measuring the Higgs boson mass, because one of the clearest Higgs decay channels involves a Higgs boson decaying into 2 Z bosons, which themselves decay into 4 muons. The 4 muons are easily identified, and their combined invariant mass reconstructs the mass of the original Higgs boson. CMS, the compact muon solenoid, employs a different design philosophy. Where ATLAS uses a large toroidal magnet system with 8 superconducting coils arranged in a barrel shape, CMS uses a single enormous solenoid producing a magnetic field of 3.8 Tesla, about 100,000 times stronger than Earth's field. This powerful magnet allows CMS to be more compact than ATLAS while achieving similar performance. CMS weighs 14,000 tons despite being smaller in volume. Its calorimeters use different technologies. The electromagnetic calorimeter is made from 76,000 lead, tungstate crystals, each a transparent block that scintillates when particles pass through. These crystals provide excellent energy resolution, allowing CMS to reconstruct the Higgs boson mass through its decay to 2 photons, with precision rivaling Atlas. The independence of the two detectors is critical. Any claimed discovery or precise measurement must be confirmed by both experiments to be trusted. Systematic errors, miscalibrations, and analysis mistakes affect each detector differently. Agreement between Atlas and CMS provides confidence that results reflect reality rather than experimental artifacts. Information extraction from collision data involves reconstructing what happened in the fleeting moment when 2 protons collided. The collision lasts about 10 to the power of -24 seconds. In that instant, the protons, each containing 3 quarks, bound by gluons, momentarily convert their kinetic energy into mass through Einstein's E equals mc². This mass can take the form of any particle allowed by quantum mechanics and energy conservation. Most collisions produce ordinary particles, quarks and gluons that fragment into jets of hadrons. But rare collisions, perhaps 1 in 10 billion, produce a Higgs boson. The Higgs immediately decays within 10 to the power of -22 seconds into other particles. Physicists never observe the Higgs directly. They infer its existence by observing its decay products and working backward to reconstruct the parent particle's properties. The Higgs boson can decay through multiple channels. About 58% of the time it decays into a bottom quark-antiquark pair. About 21% of the time into a pair of W bosons. About 6% into a tau-lepton pair. About 3% into a Z boson pair. And about 0.2% into 2 photons. Each channel has advantages and disadvantages for measurement. The bottom quark channel has the highest rate, but suffers from large backgrounds, because ordinary proton collisions produce bottom quarks copiously through strong force processes. The W and Z boson channels involve complex final states with multiple particles, challenging to reconstruct but providing distinctive signatures. The diphoton channel, despite its low rate, provides the cleanest measurement of the Higgs mass because photons can be measured with excellent energy resolution and relatively little background. Characteristic scales emerge from the data that determine vacuum stability. The Higgs boson mass of 125.25 GeV defines the energy scale of electroweak symmetry breaking, the transition in the early universe when the Higgs field acquired its non-zero vacuum expectation value. The top quark mass of 172.76 GeV sets the scale of the largest Yukawa coupling, the strength with which a fermion couples to the Higgs field. These two masses, combined with the measured strengths of the electromagnetic, weak and strong forces at electroweak energies, provide the initial conditions for extrapolating to high energies using renormalization group equations. The fine structure constant at the Z boson mass scale is approximately 1 divided by 188. The strong coupling constant at the same scale is approximately 0.118. The weak mixing angle, which relates the strengths of different weak force components, has a sine-squared value of approximately 0.23. All of these quantities have been measured to precisions of 0.1 to 1% through decades of experiments at multiple facilities. Independent confirmation of vacuum metastability comes from combining measurements across different experiments and different techniques. The top quark mass has been measured at the Tevatron at Fermilab using data from the 1990s and 2000s, and at the LHC using data from 2010 onward. The Tevatron measurements gave values around 173 GeV, with uncertainties of about 1 GeV. LHC measurements with 10 times more collision data reduced uncertainties to about 0.3 GeV. Different methods give consistent results. Direct reconstruction, where physicists identify the decay products of the top quark and calculate the invariant mass, yields one value. Template methods, where the distribution of reconstructed masses is compared to simulated distributions for different true masses, yield another. Matrix element methods, which calculate the full probability for each event based on the underlying quantum mechanics, provide a third approach. All agree within uncertainties, indicating systematic errors are well understood. The Higgs mass measurement similarly benefits from multiple channels and multiple experiments. ATLAS measures the Higgs mass through the diphoton channel, obtaining a value around 125.4 GeV. Through the 4-lepton channel involving Z boson decays, ATLAS measures approximately 124.5 GeV. CMS measures 125.0 GeV from diphotons and 125.6 GeV from 4 leptons. The differences are small within the quoted uncertainties for each channel. Combining all channels in both experiments, accounting for correlations in systematic uncertainties, yields the world average of 125.25 GeV with an uncertainty of 0.17 GeV. This combination involves sophisticated statistical techniques to properly weight different measurements and avoid double-counting information that appears in multiple analyses. The agreement between different channels, different experiments, and different analysis techniques gives confidence that the measurement reflects the true Higgs mass, rather than some artifact of any single method. Recent advances have pushed measurement precision to remarkable levels. In 2019, ATLAS published a measurement of the Higgs boson mass using the full dataset collected during Run 2 of the LHC from 2015 to 2018. This dataset contained about 150 inverse femtobarns of collision data, roughly 5 times more than Run 1. The increased statistics allowed ATLAS to reduce uncertainties by factors of 2 or more in some channels. Improvements in detector calibration, better understanding of systematic effects, and refined analysis techniques contributed additional gains. The dominant uncertainty in the Higgs mass measurement is now systematic rather than statistical. Statistical uncertainty, arising from the finite number of observed events, decreases as the square root of the number of events. Doubling the data reduces statistical uncertainty by about 40%. But systematic uncertainties arising from detector calibrations, background estimates, and theoretical models do not decrease with more data unless the understanding of these effects improves. Precision improvements in the top quark mass face different challenges. The mass of a quark is not a directly observable quantity because quarks are never found in isolation. They are always confined inside hadrons by the strong force, which becomes stronger at large distances. When you try to separate quarks, the energy invested in pulling them apart eventually creates new quark-antiquark pairs from the vacuum, producing more hadrons rather than isolated quarks. What physicists measure at colliders is not the fundamental mass parameter in the Lagrangian, the so-called Lagrangian mass, but an effective mass defined through some prescription for reconstructing quark properties from hadron observables. Different prescriptions give slightly different mass values. The differences can be several GeV, much larger than the experimental uncertainties. This ambiguity in defining the top quark mass introduces an irreducible uncertainty into vacuum stability calculations. Theorists have worked to clarify these issues. The MS-bar mass, defined through a specific renormalization scheme called modified minimal subtraction, is the most theoretically clean definition. It is the quantity that appears in renormalization group equations and that determines the running of couplings to high energies. But the MS-bar mass cannot be measured directly. It must be extracted from measurements of other quantities, like the kinematic mass reconstructed from decay products, using theoretical calculations that relate different mass definitions. These calculations involve quantum chromodynamics, corrections at next to leading order and beyond, requiring multi-loop Feynman diagram evaluations that can take years of work. Current estimates suggest the MS-bar top quark mass is approximately 162 GeV, about 11 GeV lower than the kinematic mass of 173 GeV, with an uncertainty of about 1 GeV arising from both experimental and theoretical sources. Future observations will further constrain vacuum stability through multiple approaches. The high luminosity LHC, scheduled to operate from the late 2020s through the 2030s, will collect 10 times more collision data than the current LHC. With 3,000 inverse femtobarns of data, statistical uncertainties in the Higgs mass will become negligible compared to systematics. Improvements in detector technology and calibration techniques may reduce systematic uncertainties by factors of 2, potentially reaching precisions of 0.05 GeV or better. Similar improvements in the top quark mass measurement could reduce its uncertainty below 0.2 GeV. These gains would significantly constrain the possible range of instability scales, narrowing the predictions for where the Higgs potential develops a second minimum and potentially determining definitively whether the vacuum is stable or metastable. Proposed future colliders offer even greater precision. A circular electron-positron collider such as the proposed FCCE at CERN or the CEPC in China would collide electrons and positrons at energies tuned to produce Higgs and Z bosons copiously. Unlike proton collisions, which are messy because protons are composite objects, electron-positron collisions are clean. The initial state is precisely known. The entire collision energy goes into creating new particles rather than being distributed among quarks and gluons. An electron-positron Higgs factory could measure the Higgs mass to precisions of 0.01 GeV or better, 20 times more precise than current measurements. It could also measure the Higgs self-coupling directly by observing rare processes where 2 Higgs bosons are produced simultaneously. This would provide the first direct information about the shape of the Higgs potential at energies beyond the single Higgs threshold, offering a glimpse toward the instability region. A future proton-proton collider with collision energies of 100 TeV, 10 times higher than the LHC, could probe physics at energy scales approaching 10 TeV. While still far below the instability scale of 10 to the power of 11 GeV, such a collider could discover new particles that modify the running of the Higgs coupling. If new physics exists at the few TeV scale, stabilizing the vacuum through additional contributions to quantum corrections, a 100 TeV collider would find it. The absence of new physics at that scale would strengthen the case that vacuum metastability is real and that no new particles intervene between the electroweak scale and the Planck scale. This would support the idea that the standard model, augmented only by gravity, provides a complete description of physics up to Planck scale energies, with metastability being a genuine feature of nature rather than an artifact of incomplete knowledge. The precision required to resolve vacuum stability exceeds anything attempted in science before. We are asking whether a mathematical quantity, the Higgs self-coupling at energies of 10 to the power of 11 GeV, is positive or negative. The answer depends on measurements of masses at energies of 100 GeV, 10 orders of magnitude lower, combined with theoretical calculations of quantum corrections extending over those 10 orders of magnitude. Errors anywhere in this chain propagate and accumulate. Achieving certainty requires not just better measurements, but also better calculations, including 4-loop and 5-loop corrections currently beyond reach. It requires better understanding of how to define quark masses in ways that minimize theoretical ambiguities. It requires checking the extrapolation procedure against any experimental constraints available at intermediate energies. Cosmic rays offer one such constraint. the highest energy cosmic ray ever detected, observed in 1991 and nicknamed the "Oh my God" particle, carried energy of approximately 3 times 10 to the power of 20 electron volts, about 50 joules. This is 20 million times higher than LHC collision energies. Cosmic rays at these extreme energies strike Earth's atmosphere occasionally, perhaps once per square kilometer per century. They produce cascades of secondary particles detectable by ground-based arrays. The Pierre Auger Observatory in Argentina, covering 3,000 square kilometers with particle detectors and fluorescence telescopes, observes dozens of ultra-high energy cosmic rays each year. If the vacuum were immediately unstable at energies accessible to these cosmic rays, collisions in the atmosphere might nucleate decay bubbles. The fact that we still exist places constraints. The vacuum must be stable at least up to energies of 10 to the power of 20 eV, about 10 to the power of 11 GeV. This is right at the predicted instability scale. Cosmic ray constraints are consistent with metastability, but do not rule it out because the predicted tunneling rate is so low that even billions of high-energy collisions over Earth's history would be unlikely to trigger decay. These measurements, refined over decades through technological marvels and intellectual ingenuity, reveal the parameters that determine reality's ultimate stability. But examining specific instances where these measurements have been applied and what anomalies have emerged shows that our understanding remains incomplete. The case studies revealing the fragility of vacuum stability predictions began appearing in the immediate aftermath of the Higgs discovery. In late 2012, just months after the July announcement, Giuseppe de Grassi led a collaboration that published their analysis in the Journal of High Energy Physics. They took the preliminary Higgs mass measurement of 125 GeV and the then current top quark mass measurement of 173.2 GeV and calculated the fate of the universe. Their paper, which would be cited thousands of times, concluded that with these values, the electroweak vacuum is metastable. The Higgs self-coupling turns negative at an energy scale they estimated as roughly 10 to the power of 11 GeV. The expected lifetime of the false vacuum, they calculated, exceeded 10 to the power of 100 years. But the paper contained a crucial caveat. If the top quark mass were actually 171.4 GeV instead of 173.2 GeV, just 1.8 GeV lighter, and within the measurement uncertainties at that time, the vacuum would be absolutely stable. The fate of the universe hinged on a mass difference smaller than 1%. A contrasting study appeared in 2013 from Dario Buttazzo and collaborators. They used refined measurements incorporating additional data from both the LHC and the Tevatron. Their analysis included more sophisticated 3-loop calculations and improved estimates of theoretical uncertainties. They found the situation even more precarious than de Grassi's group. According to their calculations, the critical top quark mass, separating stability from metastability, was 171.5 GeV. The measured value of 173.2 GeV placed the universe firmly in the metastable regime, but not deeply. If measurements shifted by just 2 GeV due to better calibrations or refined systematic error estimates, the conclusion could reverse. They emphasized that the vacuum sits remarkably close to the critical boundary, closer than would be expected if parameters were chosen randomly from any natural distribution. What makes these studies special is not just their calculations, but the divergent conclusions reached despite using similar methods and data. A 2014 analysis by Alekin, Djawadi, and Moch took a more conservative approach to estimating uncertainties. They argued that theoretical errors in the 3-loop calculations, particularly in how the strong coupling constant runs with energy, introduced larger uncertainties than previous groups had acknowledged. When they inflated the error bars appropriately, they found the instability scale could range from as low as 10 to the power of 8 GeV to as high as 10 to the power of 15 GeV. This enormous range encompassed scenarios where the vacuum is clearly unstable, barely metastable, or possibly stable. Their conclusion was that based on 2014 measurements, we simply could not determine the vacuum's fate with confidence. The precision was insufficient. The theory was incomplete. Recent discoveries have narrowed these uncertainties but not eliminated them. In 2019, the CMS collaboration published a comprehensive measurement of the top quark mass using 137 inverse femtobarns of collision data, the full Run-2 dataset from 2015 to 2018. They employed multiple reconstruction techniques, comparing results from direct kinematic methods, template fits, and ideogram approaches. Their final value was 172.25 GeV, with an uncertainty of 0.61 GeV, combining statistical and systematic errors. This was significantly more precise than earlier measurements. Separately, a combination of multiple Tevatron and LHC measurements published in 2019 gave 172.76 GeV with an uncertainty of 0.30 GeV. The two values differed by 0.5 GeV, nearly 2 standard deviations, suggesting some systematic effect was not fully understood. If the true mass lies closer to the CMS value of 172.25 GeV, the vacuum is more stable than standard model extrapolations using 172.76 GeV would suggest. If it lies at 172.76 GeV or higher, metastability becomes more certain. The Higgs mass measurements show similar patterns of convergence with residual tensions. Atlas published their Run-2 Higgs mass measurement in 2020, obtaining 124.97 GeV with an uncertainty of 0.24 GeV from the diphoton channel, and 124.79 GeV with an uncertainty of 0.37 GeV from the 4-lepton channel. CMS obtained 125.38 GeV with an uncertainty of 0.40 GeV from diphotons. The Atlas and CMS diphoton results differ by 0.4 GeV, about 1.5 standard deviations. Again, this suggests systematic effects dominate the error budget and that true precision has not yet been achieved. Different detector responses to photons, different methods of calibrating energy scales, different background subtraction techniques all introduce systematic uncertainties that are difficult to quantify accurately. The quoted uncertainties may underestimate the true measurement errors. Comparative analysis across different theoretical approaches reveals deeper tensions. Lattice QCD calculations, which should in principle yield the same vacuum stability predictions as perturbative calculations if both are done correctly, have produced conflicting results. A 2015 lattice study by Fodor and collaborators calculated the Higgs self-coupling at high energies by discretizing spacetime into a lattice with spacing of about 0.1 femtometers and computing the path integral numerically. They found that lattice artifacts, errors introduced by the finite lattice spacing, were larger than initially expected. After attempting to extrapolate to 0 lattice spacing, they obtained results suggesting the instability scale might be lower than perturbative calculations predicted, around 10 to the power of 9 GeV instead of 10 to the power of 11 GeV. But their error bars were large, and subsequent lattice studies obtained different results. A 2018 lattice study by Greensight and collaborators used improved lattice actions, mathematical formulations that reduced discretization errors, and finer lattice spacings. They found the opposite trend. Their results suggested the instability, if it exists, appears at higher energies than perturbative calculations predicted, possibly above 10 to the power of 13 GeV. This would make the vacuum more stable, increasing the expected lifetime substantially. However, their systematic uncertainties were also large. The discrepancy between lattice studies and between lattice and perturbative approaches indicates that calculating vacuum stability remains at the edge of what current theoretical methods can achieve reliably. We are pushing both perturbative and non-perturbative techniques into regimes where their approximations begin to fail. Similar phenomena to vacuum metastability appear throughout physics, offering analogies and insights. Supercooled liquids and glasses provide one example. A glass is a liquid that has been cooled below its freezing point without crystallizing. It remains in an amorphous, disordered state rather than forming the ordered crystalline structure that would have lower energy. The glass is metastable. Over extremely long timescales, millions of years or more, glasses can slowly crystallize, transitioning to the true minimum energy state. Ancient Roman glass shows microscopic crystallization that accumulated over 2 millennia. The vacuum is analogous. It persists in a higher energy configuration because transitions to the lower energy configuration are rare, requiring quantum tunneling rather than thermal activation, but following similar statistical patterns. Magnetic systems offer another analogy. Ferromagnets have multiple magnetic ground states, with the magnetization pointing in different directions. A ferromagnet can be trapped in a metastable state, where domains of magnetization point in different directions, creating a configuration with higher energy than a fully aligned state. Thermal fluctuations or quantum tunneling can flip domains, gradually converting the metastable configuration towards the ground state. The dynamics of domain wall motion in ferromagnets, where regions of different magnetization meet and evolve, resembles the dynamics of vacuum decay bubble walls. Both involve interfaces between different states of matter or fields, with surface tension resisting motion and energy differences driving it. Statistical distribution of parameters in the standard model reveals curious patterns. If you plot all possible values of the Higgs and top quark masses on a two-dimensional graph, you can divide the plane into regions corresponding to stable vacuum, metastable vacuum, and unstable vacuum. The measured values place us just inside the metastable region, very close to the boundary with the stable region. The probability of landing in this specific location by chance, if masses were chosen randomly, is low but not impossibly so. Estimates suggest perhaps 10 to 20% of parameter space that is consistent with life, and observers corresponds to metastability with very long lifetimes. So while the precise values seem fine-tuned, they may not be as improbable as they first appear if one accounts for anthropic selection effects. But here is an unexplained aspect that troubles theorists. Not only are we close to the stability boundary in Higgs top mass space, we are also close to several other boundaries simultaneously. The cosmological constant is small but non-zero, sitting about 120 orders of magnitude below its natural scale. The Higgs vacuum expectation value is about 16 orders of magnitude below the Planck scale, separated by a large hierarchy with no intermediate scales. The strong CP problem, another fine-tuning issue involving why the strong force conserves charge parity symmetry to high precision, suggests another parameter that is unnaturally small. We appear to live in a universe where multiple parameters are tuned to sit near critical boundaries. Explaining one fine-tuning through anthropic reasoning might be acceptable. Explaining several independent fine-tunings simultaneously becomes problematic. Either we are extraordinarily lucky, or some deeper principle constrains these parameters in ways we do not yet understand. Ongoing research explores several directions attempting to resolve these puzzles. One approach involves searching for additional particles at the LHC that might modify vacuum stability. Experiments continue looking for evidence of supersymmetry, additional Higgs bosons, heavy right-handed neutrinos, leptoquarks, and various other hypothetical particles. Each would contribute quantum corrections to the running of the Higgs self-coupling. A new particle at a few TeV with the right properties could eliminate the instability entirely. The absence of any signal so far suggests either these particles do not exist at accessible masses, or they exist but have properties that make them difficult to detect. Some supersymmetric models predict particles that interact very weakly with ordinary matter, making them nearly invisible to detectors. Others predict particles that decay rapidly into final states mimicking standard model backgrounds. Sophisticated search strategies using machine learning algorithms to distinguish signal from background continue to improve, and the full Run 2 dataset is still being analyzed with refined techniques. Another research direction involves precision calculations of higher-order corrections. Computing for-loop contributions to renormalization group equations requires evaluating Feynman diagrams with enormous complexity. A single for-loop diagram might involve hundreds of terms, each requiring numerical integration over multiple momentum variables. Advances in computer algebra systems and symbolic integration techniques have made some for-loop calculations feasible. A partial for-loop analysis of the Higgs self-coupling running, published in 2017 by a collaboration including Chatterkin and Zoller, found that for-loop corrections changed the predicted instability scale by about 15% compared to 3-loop results. This is significant, but not decisive. Full for-loop calculations, including all relevant diagrams and properly accounting for scheme dependencies, remain years away. 5-loop calculations, which might be needed for percent-level precision in the instability scale prediction, are likely decades away given current computational capabilities. Cosmological observations offer indirect constraints on vacuum stability through observations of the early universe. The cosmic microwave background, measured by the Planck satellite mission with exquisite precision, provides a snapshot of the universe 380,000 years after the Big Bang. The statistical properties of temperature fluctuations in the CMB depend on the physics of the very early universe, particularly the inflationary epoch. If the Higgs field played a role in inflation, its potential at high field values would affect inflationary predictions. Some models of Higgs inflation require the Higgs potential to have specific properties at energies around 10 to the power of 14 GeV. These properties can be compatible with vacuum metastability, but the connection is subtle and model-dependent. Future CMB observations from experiments like CMB-S4, planned for the late 2020s, will measure polarization patterns in the microwave background with unprecedented sensitivity, potentially detecting the signature of gravitational waves from inflation. These measurements could constrain the energy scale and dynamics of inflation, indirectly informing our understanding of the Higgs potential at high energies. Gravitational wave observations might also contribute unexpectedly. If vacuum decay occurred in the early universe, creating bubbles that collided and merged as they expanded, those collisions would have generated gravitational waves with characteristic frequencies and amplitudes. The Laser Interferometer Space Antenna, or LISA, scheduled for launch in the mid-2030s, will detect gravitational waves at millihertz frequencies, complementing the higher frequency detections made by LIGO and Virgo. LISA will be sensitive to gravitational waves from phase transitions in the early universe, including potentially from vacuum transitions. A detection would revolutionize our understanding of cosmic history. Non-detection would place constraints on how often such transitions occurred, or whether they occurred at all, providing evidence that the vacuum has been stable or metastable without undergoing transitions throughout cosmic history. The statistical analysis of cosmic structure also bears on vacuum stability indirectly. The distribution of galaxies, galaxy clusters, and voids in the universe depends on the physics of structure formation. Dark matter clumping under gravity, opposed by dark energy's repulsive effect, creates the cosmic web we observe. If the vacuum underwent a transition at some point in cosmic history, even locally in some region we cannot observe, it might have left signatures in the statistical properties of large-scale structure. Anomalies in the galaxy distribution, unexpected features in the matter-power spectrum, or violations of cosmological isotropy could hint at past vacuum dynamics. Current surveys like the Dark Energy Spectroscopic Instrument, or DESI, which began observations in 2021, are mapping tens of millions of galaxies to unprecedented precision. These maps will reveal subtle features in the cosmic structure that might constrain exotic scenarios, including vacuum transitions. Each of these research directions remains active. Experimental programs at the LHC continue through at least the 2030s. Theoretical calculations push toward higher precision. Cosmological observations accumulate data revealing the universe's history and structure. None have yet resolved whether the vacuum is truly metastable or whether measurements and calculations will eventually converge on stability. The question remains open. What we do know is that current evidence places us remarkably close to a critical boundary, closer than comfort would suggest, in a configuration where the fundamental structure of reality appears temporary rather than eternal. This proximity to criticality, observed across multiple independent parameters, suggests our cosmic situation may be more special or more typical than simple randomness would predict. Understanding why our measurements place us in this particular configuration and what that implies about the nature of physical law and our cosmic context requires examining how observational biases and our particular perspective might be shaping what we see. The observational biases shaping our understanding of vacuum stability begin with a fundamental limitation. We can only measure physics in our immediate cosmic neighborhood. The observable universe extends roughly 46 billion light-years in all directions, a vast distance containing perhaps 2 trillion galaxies. But this represents only a tiny fraction of the total universe, which may be infinite in extent. Beyond our cosmic horizon, causally disconnected from us by the expansion of space, lies an unknowable expanse where conditions might differ dramatically. We observe physics in one location, at one moment in cosmic time, and we assume those observations generalize to the entire universe across all of time. This assumption, called the cosmological principle, states that the universe is homogeneous and isotropic on large scales. No location is special, no direction is preferred. The laws of physics are the same everywhere. But this principle is an assumption, not a proven fact. How perspective affects our measurements becomes clear when we consider what it means to measure a fundamental constant. When physicists measure the fine structure constant, they create electromagnetic interactions in a laboratory or observe them in distant galaxies and extract the coupling strength. That measured value represents the fine structure constant in our vacuum state, at our cosmic time in our local gravitational environment. If the vacuum were different elsewhere, the constant would differ. If we lived inside a vacuum decay bubble that had formed billions of years ago, expanding to encompass our entire observable universe, we would measure different values for all constants and never know we were in a bubble. The physics we observe would seem natural and universal to us, having never experienced anything else. We would have no reference point for comparison. This creates what physicists call the bubble problem. Suppose vacuum decay occurred somewhere in the universe long before our solar system formed. The bubble expanded at light speed, but the universe also expanded. If cosmic expansion was rapid enough, the bubble might never catch up to distant regions. Those regions remain in the original vacuum state. Our observable universe could lie entirely within the bubble, having undergone the transition billions of years ago. We would be in the true vacuum, measuring its properties, completely unaware that a false vacuum exists elsewhere beyond our horizon. Alternatively, we might be in the false vacuum while bubbles of true vacuum have formed in distant, unobservable regions. Our measurements tell us about our local vacuum state, but reveal nothing about the global structure of vacuum configurations across the cosmos. The concept gains concrete implications through an example. Imagine vacuum decay occurred 10 billion years ago at a location that was then 1 billion light-years away from the matter that would eventually form our galaxy. The bubble expanded outward at light speed. In a non-expanding universe, the bubble would reach us after 1 billion years of travel. But the universe expands. As the bubble wall moved toward us, the space between the wall and our location stretched. Whether the bubble overtakes us depends on the expansion rate. If the expansion rate remains constant, the bubble catches up eventually. If expansion accelerates, which it does in our universe due to dark energy, the bubble might never reach us. The accelerating expansion of space can carry distant regions away from us faster than light moves through that expanding space. A bubble wall, traveling at light speed but fighting against cosmic expansion, might advance toward us while simultaneously receding in co-moving coordinates. Calculations show that for the measured value of dark energy and the observed expansion rate, vacuum decay bubbles could exist within our cosmic horizon but beyond our detection capabilities. A bubble forming anywhere more than about 10 billion light-years away in co-moving distance would be invisible to us if it formed within the past 13.8 billion years. The light from the bubble wall's formation, carrying information about the transition, would not have had time to reach us. Meanwhile, the bubble continues growing, but remains beyond our observable universe's boundary. We might be surrounded by bubbles of true vacuum in all directions, with bubble walls advancing toward us from multiple angles, and we would have no way to detect them until they arrive. This prospect is both fascinating and unsettling. The universe might be far more varied than we observe, with vast regions in different vacuum states separated by expanding walls of destroyed physics. The typicality versus specialness debate centers on whether our vacuum parameters are generic or unusual. Typicality would suggest that most observers in the universe measure vacuum properties similar to ours. If we are typical, then most of the universe exists in our vacuum state, and our measurements reflect the common cosmic condition. Specialness would suggest we occupy an unusual location or time, where vacuum properties differ from the cosmic average. The vacuum metastability, combined with our proximity to the stability boundary, argues against typicality. If most regions of the universe were metastable with parameters exactly like ours, that would represent an enormous coincidence. Why should the Higgs and top quark masses, which could, in principle, take any values across a wide range, conspire to place most observers near a critical boundary? Cosmological principles are at stake in this debate. The Copernican principle, named for Nicholas Copernicus, who demonstrated that Earth is not the center of the solar system, states that we do not occupy a special position in the cosmos. Copernicus dethroned Earth from its central position. Later observations showed the Sun is not the center of the galaxy. The galaxy is not the center of the universe. We exist in a typical location within a typical galaxy within a typical region of space. Extending this principle to vacuum physics would suggest our measured constants are typical, representative of the universe at large. But the fine-tuning of parameters for vacuum metastability challenges this extension. Either we are not typical, violating the Copernican principle, or the universe contains mechanisms that naturally produce observers near critical boundaries, making such configurations typical despite seeming unlikely. Historical context reveals that the Copernican principle has been tested and refined repeatedly. In the 1920s, Edwin Hubble discovered that galaxies are receding from us, with more distant galaxies receding faster. This observation is consistent with the cosmological principle. Every observer in the expanding universe sees all other galaxies receding, so no location is special. But Hubble's observations also revealed that the expansion rate, measured through what is now called the Hubble constant, has a specific value of approximately 70 kilometers per second per megaparsec. This value determines the age of the universe, the size of the observable region, and the properties of cosmic structure. Is this value typical? Or do different regions of the universe, or different universes in a multiverse, have different expansion rates? We cannot answer without observations beyond our horizon. In the 1960s, Robert Dicker and others developed anthropic reasoning to address fine-tuning puzzles. Dicker noted that the age of the universe we observe is not arbitrary. We observe the universe at an epoch when stars exist, because stars are necessary for carbon-based life. Stars have finite lifetimes, so we necessarily find ourselves observing the cosmos during the era when stars shine. This is a selection effect. It does not explain why stars exist or why the universe has properties that allow stars to form. But it does explain why we observe the universe at this particular age, rather than much earlier or much later. Applying similar reasoning to vacuum stability suggests we observe a metastable vacuum with a long lifetime because vacuums with short lifetimes do not allow observers to emerge. But this does not explain why any vacuums have long lifetimes, or why our parameters place us so close to the critical boundary. Anthropic considerations can explain bounds, but not precise values. The requirement that atoms form, that stars shine, that chemistry works, places constraints on possible values of fundamental constants. If the electromagnetic force were much stronger, electrons would fall into atomic nuclei. If it were much weaker, atoms would be too large and diffuse to form stable molecules. These anthropic constraints exclude vast regions of parameter space, but they do not uniquely predict the observed values. Many combinations of constants would allow complex chemistry and life. We observe one particular combination. Why this one? Anthropic reasoning offers no answer unless combined with the assumption of a multiverse where all allowed combinations exist somewhere, and we necessarily observe one compatible with our existence. The vacuum metastability adds a temporal dimension to anthropic reasoning. Not only must the vacuum allow complex structures to form, it must remain stable long enough for those structures to emerge and evolve. A vacuum with a lifetime of only 1 million years would allow atoms and simple molecules, but not stars or planets. A vacuum lasting 1 billion years would allow stars, but not the billions of years needed for biological evolution on planets. Our vacuum has lasted at least 13.8 billion years, long enough for galaxies, stars, planets, and life to emerge. The calculated expected lifetime of 10 to the power of 100 years or more vastly exceeds what anthropic requirements demand. This seems like overkill. A vacuum lasting 10 billion years would suffice for observers. Why is ours stable for so much longer? Either we are extraordinarily lucky, or the mechanism producing long-lived vacuums tends to produce very long lifetimes, with 10 billion years, and 10 to the power of 100 years being similarly likely outcomes of whatever process selects vacuum properties. Future surveys aim to test these ideas by mapping the universe's large-scale structure and searching for anomalies. The Dark Energy Spectroscopic Instrument began its 5-year survey in 2021, measuring redshifts for approximately 35 million galaxies and quasars. This will create a 3-dimensional map of the universe spanning 11 billion years of cosmic history. If vacuum properties varied across this volume, if we lived near a boundary between different vacuum regions, the survey might detect irregularities in the galaxy distribution. A sudden change in structure properties at some distance could indicate a transition occurred in the past at that location. Alternatively, statistical analyses might reveal that our local region is unusual compared to the cosmic average, suggesting we occupy a special location rather than a typical one. The Vera Rubin Observatory, scheduled to begin operations in the mid-2020s, will conduct the Legacy Survey of Space and Time, photographing the entire visible sky every few nights for 10 years. This will detect billions of galaxies, track supernovae and other transient events, and measure how the universe's expansion rate changes over time. If vacuum properties are evolving, if we are slowly transitioning toward a decay, or if distant regions are undergoing transitions invisible to us now, the survey might detect subtle effects on cosmic expansion. The gravitational influence of energy density variations associated with vacuum transitions could create observable features in the growth of cosmic structure over billions of years. These surveys treat the universe as a natural laboratory for testing fundamental physics. We cannot build accelerators energetic enough to probe the instability scale directly. We cannot create conditions in laboratories matching the early universe when temperatures exceeded 10 to the power of 15 Kelvin. But the universe itself reached those conditions. The cosmic microwave background carries information from 380,000 years after the Big Bang. Gravitational waves might carry information from even earlier, perhaps from 10 to the power of minus 35 seconds after the beginning when inflation occurred. By observing the universe at different epochs and different scales, we effectively probe physics at energies unattainable on Earth. The universe is our laboratory for quantum field theory at extreme energies, for quantum gravity near the Planck scale, for understanding the Higgs potential where it develops its second minimum. But this laboratory has limitations. We observe only one universe, one realization of cosmic history. In particle physics experiments, we collide billions of particles and measure statistical distributions. We repeat experiments under controlled conditions to separate signal from noise. The universe offers no such opportunities. We cannot rerun cosmic history. We cannot observe multiple universes to measure variation. We see one outcome of one set of initial conditions, evolved through one realization of quantum fluctuations. Extracting general principles from a single observation is extraordinarily difficult. Cosmologists must assume that the regions we observe are representative of the whole, that our cosmic horizon contains typical rather than unusual examples of cosmic phenomena. But we cannot verify this assumption without observing beyond our horizon, which is impossible. The question of whether we can determine the vacuum's true stability from observations within our bubble is therefore deeply philosophical. If we are in a false vacuum that has persisted for 13.8 billion years, observations tell us it is metastable with at least that lifetime. If we are in a true vacuum, having undergone a transition before our observable universe formed, observations tell us nothing about the original false vacuum. If we are in a true vacuum and false vacuum never existed, observations correctly indicate stability. 3 distinct physical scenarios produce similar observations, distinguished only by history we cannot access. The meta-stability calculations based on measured particle masses predict what would happen if our current vacuum is false. They cannot tell us whether it actually is false, or whether we already transitioned to truth long ago. This uncertainty reflects a deeper issue about the nature of scientific knowledge. Physics operates by constructing mathematical models that explain observations and predict new phenomena. When predictions match observations, we gain confidence in the model. But matching observations is necessary, not sufficient. Multiple models might explain the same observations equally well. Discriminating between them requires finding observable consequences where the models differ. For vacuum stability, most observable consequences lie beyond our reach. The instability scale is too high for accelerators. Vacuum decay, if it occurs, will not happen in our lifetimes or for billions of generations. We predict the far future based on theory, not observation. Theory is well tested at accessible energies but extrapolated over vast scales to predict what happens at energies we cannot probe. This extrapolation introduces uncertainties that accumulate the farther we push beyond known territory. Our cosmic situation resembles ancient astronomers inferring the structure of the solar system from observing planetary motions. They could measure positions and velocities, but they could not visit other planets to verify their models directly. They developed theories geocentric and heliocentric that explained observations. Discrimination required increasingly precise measurements and sophisticated reasoning. We face similar challenges. We measure particle masses and coupling constants in our laboratories on Earth. We infer the shape of the Higgs potential at energies 15 orders of magnitude higher. We predict the lifetime of the vacuum and the possibility of decay. But we cannot verify directly. We cannot probe those energies. We cannot witness decay and confirm our predictions. We must trust that the mathematical framework relating low-energy measurements to high-energy phenomena is reliable, that quantum field theory remains valid across those energy scales, that no new physics intervenes to modify our extrapolations. The reliability of this trust varies across the scientific community. Some physicists view vacuum metastability as a robust prediction following inevitably from measured parameters and well-tested theory. Others view it as speculative, an artifact of pushing calculations beyond their regime of validity. The debate will continue until either new measurements shift parameters decisively into stable or unstable regions, or new physics is discovered that modifies the vacuum stability calculation, or future observations detect consequences of vacuum transitions in cosmological data. Until then, we live with uncertainty. We inhabit a universe where the fundamental stability of physical law remains an open question, where the parameters we measure suggest, but do not prove, that the vacuum supporting our existence might be temporary, and where our inability to observe beyond our cosmic horizon prevents us from determining whether we are typical or special in the grand cosmic scheme. The long-term implications of this uncertainty and what vacuum metastability means for the ultimate future of the cosmos and any life or intelligence that might exist billions or trillions of years from now, demand consideration even as the answers remain shrouded in the fog of what we cannot yet measure. The long-term evolution of the universe under a metastable vacuum unfolds across timescales that dwarf human comprehension. Begin with what we know. The Sun will exhaust its hydrogen fuel in approximately 5 billion years. It will expand into a red giant engulfing Mercury and Venus, possibly reaching Earth's orbit. The outer planets will survive, their orbits pushed outward by the Sun's mass loss. After another billion years as a red giant, the Sun will shed its outer layers, creating a planetary nebula surrounding a white dwarf core. That core will cool slowly over trillions of years, fading from white to yellow to red to black as it radiates away its residual heat. This is the fate awaiting most stars like our Sun. Smaller stars burn slower and last longer. the smallest red dwarfs might shine for 10 trillion years or more before exhausting their fuel. But stellar lifetimes are brief compared to cosmic timescales relevant to vacuum decay. In 100 trillion years, approximately 10 to the power of 14 years, star formation will effectively cease. The gas clouds from which stars form will be depleted. Existing stars will burn out one by one. Galaxies will darken as their stellar populations age and die without replacement. The universe will enter what cosmologists call the degenerate era, dominated by stellar remnants. White dwarfs, neutron stars, and black holes will be the primary objects. These remnants will cool and fade, emitting ever less radiation as their temperatures drop toward absolute zero. Occasional stellar collisions in dense regions might reignite fusion temporarily, producing brief flashes of light in an otherwise dark cosmos. The universe will continue expanding throughout this era. Dark energy, the mysterious component driving accelerated expansion, shows no sign of diminishing. If it remains constant, as current observations suggest, then the expansion will accelerate forever. Galaxies outside our local group, already receding from us, will continue accelerating away. Their light will redshift beyond detectability. One by one, they will cross our cosmic horizon, disappearing from view as they recede faster than light can travel through expanding space. In perhaps 100 billion years, every galaxy beyond our local gravitationally bound cluster will have vanished beyond the horizon. An observer in the Milky Way at that time would see only nearby galaxies. The rest of the universe would be invisible, not because it ceased to exist, but because light from it can no longer reach us. This isolation has profound implications for future civilizations. Any intelligence arising in the distant future, long after galaxies have separated beyond visibility, would observe a universe containing only their local cluster. They would see no cosmic expansion beyond local scales. They would have no access to the cosmic microwave background, which will have redshifted to undetectable wavelengths. They would lack the observational evidence that revealed the Big Bang, cosmic expansion, and the universe's large-scale structure to 20th century astronomers. Their cosmology would be impoverished, their understanding of the universe's history and scope fundamentally incomplete. They would live in a universe far larger and older than they could ever know. This demonstrates how contingent scientific knowledge is on the observational windows available at any given epoch. Vacuum decay places an additional, starker limitation on cosmic futures. If the vacuum is metastable with an expected lifetime of 10 to the power of 100 years, then long before stellar remnants cool completely, long before black holes evaporate, the vacuum could decay. When it does, everything changes instantly across the expanding bubble. The constants determining particle masses would shift. The forces binding atomic nuclei would alter in strength. Complex structures built from atoms and molecules, including any technological artifacts or organized information storage systems, would disintegrate as the rules changed. Not gradually, not with warning, but as fast as the bubble wall expands. One moment, atoms exist and obey familiar laws. The next moment, different laws apply, and those atoms cannot exist in their previous form. The implications for life extend beyond simple extinction. Biological life requires chemistry, and chemistry requires atoms with stable electron configurations. Change the electromagnetic force strength by a few %, and electron orbits shift. Atomic radii change, bond energies change. The molecules supporting biochemistry, DNA, proteins, lipids, all depend on precise force strengths. A different vacuum with different constants might not allow carbon atoms to form 4 bonds, might not allow water to be liquid at reasonable temperatures, might not permit the formation of complex organic molecules. Life as we know it requires the specific vacuum state we inhabit. Change that state and life ends, not through starvation or cold or radiation, but through the fundamental impossibility of the chemical processes that define living systems. Advanced civilizations, if any exist in the distant future, might attempt to detect vacuum decay approaching. They could monitor distant regions of space for anomalies, for changes in spectroscopic patterns indicating altered constants. But the detection window is narrow. Light from a forming bubble travels at the same speed as the bubble wall itself. Any warning signal arrives at most moments before the destruction it announces. An observer 1 light year from a forming bubble would detect its radiation 1 year before the wall arrives. They would have 1 year to understand what was coming, 1 year to prepare or to record their existence somehow. But there is nowhere to flee. The bubble expands in all directions. Even traveling at near light speed, escape is impossible. The bubble catches everything within its reachable volume eventually. Some theoretical proposals suggest advanced civilizations might influence vacuum stability. If the tunneling rate depends on local energy densities or quantum field configurations, perhaps sufficiently advanced technology could stabilize the vacuum in a region of space, creating a protective domain resistant to decay. This remains pure speculation. We understand so little about quantum field theory at extreme energies that predicting what manipulation might be possible is premature. But the idea illustrates how vacuum metastability poses not just a passive threat, but potentially an active challenge for far future intelligence. Survival might require not just adapting to new environments or building robust technologies, but intervening in the fabric of space-time itself to maintain the physical laws that allow existence. Other observers, if they exist elsewhere in the universe, face the same uncertainties. The vacuum metastability is not localized. It applies universally within our vacuum domain. Every atom of oxygen in every star system across billions of light years exists because the vacuum has not yet decayed. Every observer anywhere in our cosmos depends on the same metastable configuration. If decay occurs, it threatens everyone. There is no safe haven within this universe. The only refuge would be disconnected universes in some multiverse scenario, domains with different vacuum states causally separated from ours. But we have no evidence such domains exist, and no way to reach them if they do. This raises meta-questions about the nature and limits of knowledge. Can we truly predict the far future given that fundamental physics itself might change? Astronomy and cosmology assume the laws of physics are constant in time, allowing us to extrapolate from present observations to past and future. But if the vacuum can decay, this assumption fails. The laws are temporary, valid only so long as the vacuum persists. Predictions extending beyond the vacuum lifetime become meaningless. We can describe what will happen to stars and galaxies given current physics. We cannot say whether current physics will remain valid. This introduces irreducible uncertainty into cosmological futurology. The philosophical synthesis emerging from vacuum metastability connects to ancient questions about permanence and change. Pre-Socratic philosophers debated whether the fundamental nature of reality was stable or flux. Heraclitus argued everything flows, nothing remains constant. Parmenides countered that change is illusion, and true reality is eternal and unchanging. Modern physics suggests a middle ground. The quantum fields underlying matter are eternal and unchanging in their mathematical structure. But the vacuum state those fields occupy can change. The fields persist. Their configuration does not. Physical law, in this view, is partly permanent, the field equations and symmetry principles, and partly contingent, the particular vacuum determining constants and particle masses. This duality appears throughout physics. The electromagnetic field equations written by Maxwell in the 1860s remain valid today. But the permittivity and permeability of the vacuum, the constants appearing in those equations, depend on the vacuum state. In a different vacuum, Maxwell's equations would have the same form, but different constants. Phenomena would look similar, but quantitatively different. Photons would still exist, atoms would still form, but the energy levels would shift, spectra would change, and chemistry would operate under modified rules. The deep structure persists. The surface details transform. Returning to the opening theme, the bubble of destruction could form at any moment, and we would never see it coming. This is not a distant abstraction, it is a present reality. Right now, as you hear these words, quantum fluctuations occur throughout space. Virtual particle pairs appear and vanish. The Higgs field fluctuates around its vacuum expectation value. Most fluctuations are small, brief, insignificant. But the mathematics of quantum field theory admits rare, large fluctuations that could nucleate a bubble of true vacuum. The probability is unimaginably small, but it is not zero. Every cubic meter of space in every second has a tiny chance of becoming the nucleation point for vacuum decay. Multiply by the vast volume of the universe and the billions of years of cosmic time, and the probability accumulates. Still small, still unlikely, but not impossible. We live perpetually on the edge of transformation. The apparent stability of physical law masks an underlying precariousness. Every atom, every force, every constant depends on the vacuum persisting in its current state. Change the vacuum, and you change reality itself. Not the surface features like which stars exist or where galaxies cluster, but the deep features like how electromagnetism works and what mass the electron possesses. This is instability at the most fundamental level imaginable. Not social instability or ecological instability or technological instability. Ontological instability. The categories of being itself are temporary. Yet we persist. The vacuum has not decayed. The laws continue. Stars shine. Planets orbit. Life emerges and evolves and develops technology sufficient to measure the masses of fundamental particles and calculate the stability of the vacuum. This is remarkable that a metastable universe can last long enough for observers to arise and discover their own precariousness suggests either extraordinary luck or some principle we do not yet grasp. Perhaps metastable vacuums with very long lifetimes are common in the cosmic landscape. Perhaps the anthropic selection effect is stronger than we realize, constraining observable parameters to narrow ranges. Perhaps new physics beyond the standard model intervenes to stabilize what appears unstable. We do not know. What we do know is this: the universe you observe, with its atoms and forces and constants, exists in a particular configuration. That configuration emerged from the hot Big Bang and has persisted for 13.8 billion years. It might persist for 10 to the power of 100 years more, or it might end in the next instant. The mathematics predicts but cannot determine. Quantum mechanics is probabilistic. Outcomes are uncertain until measured, and we cannot measure the vacuum's fate. We can only wait and observe. Every moment that passes without decay tells us the vacuum has lasted 1 moment longer. Every measurement confirming the same constants reassures us the laws remain unchanged. But past persistence guarantees nothing about future stability. This uncertainty is not cause for despair, it is cause for humility. Our knowledge is bounded, our predictions are probabilistic. The universe is larger, older, and stranger than we can fully comprehend. We occupy one moment in cosmic time, one location in cosmic space, with access to observations spanning a tiny fraction of the whole. From this limited vantage, we construct models, extrapolate trends, and predict the far future. Sometimes we are right. Sometimes new observations overturn decades of theory. Science progresses through this cycle of prediction and test, hypothesis and revision. Vacuum stability represents the frontier where prediction extends beyond any possible test, where extrapolation reaches energies accessible only in the universe's earliest moments, where uncertainty is irreducible because the phenomena are intrinsically probabilistic. In this uncertainty lies a kind of freedom. The future is not predetermined. Even the laws of physics might change. What seems impossible under current laws might become possible under new ones. What seems permanent might be temporary. The cosmos is not a static stage, but a dynamic arena where even the rules of the game can shift. We are participants in this cosmic drama, conscious arrangements of atoms capable of understanding their own contingency. We measure the Higgs boson mass. We calculate renormalization group equations. We predict vacuum lifetimes exceeding the current age of the universe by factors of 10 to the power of 90. And in doing so, we demonstrate that matter can organize itself into structures sophisticated enough to comprehend the foundations of reality, however precarious those foundations might be. The silence of the universe on this question, the absence of any observed vacuum decay anywhere within our cosmic horizon, is itself information. Either we are extraordinarily lucky, living in the vast expanse of time before the unlikely occurs, or the calculations overestimate the instability, or new physics stabilizes what appears unstable, or we misunderstand something fundamental. Each possibility has implications. Each suggests different lessons about the nature of the cosmos and our place within it. We live in the era where these questions can be asked but not yet answered, where technology reveals the precision of physical law while mathematics hints at its impermanence. The ultimate message is one of cosmic contingency. Nothing is guaranteed. Not the persistence of the vacuum, not the constancy of physical law, not the survival of structure and complexity over cosmic time. We exist in a moment of grace, a window where the universe is old enough for complexity to emerge but young enough for structure to persist. This window might last 10 to the power of 100 years, longer than any meaningful comprehension allows, or it might close in 0.001 seconds. We simply do not know. The mathematics gives probabilities, not certainties. And in a probabilistic universe, every outcome with non-zero probability eventually occurs somewhere, somewhen. So we look outward into the night sky, observing the light from distant galaxies, measuring the properties of particles, calculating the fate of reality itself. We reach toward understanding, knowing our grasp will always be incomplete. The universe is too large, time is too long, quantum mechanics is too fundamentally uncertain, but the reaching matters. The attempt to understand our cosmic situation, to measure the parameters determining existence, to calculate how long the laws might last, this is among the most profound expressions of human curiosity and capability. We are the universe examining itself, conscious matter investigating the foundations of matter, temporary structures studying the conditions for their own continuation. If this journey through vacuum decay and cosmic metastability spoke to you, consider subscribing to explore more cosmic mysteries that help you drift off into thoughtful sleep. There are more questions waiting, more strange features of reality to contemplate in the quiet darkness. Leave a like if you found peace in confronting uncertainty, in recognizing that even physical law is temporary, that we live in a moment of borrowed stability that could end at any instant but probably will not. And good night, wherever you are in this vast, precarious, metastable universe.